Hello there, and welcome to Physics with William, where curiosity is allowed to slow down, difficult questions are given a little room to breathe, and the stranger corners of science can be explored without needing to rush toward an answer. Tonight, we're beginning with one of the most famous thought experiments in all of physics, and perhaps the only one that has managed to make a household pet into an international symbol of quantum mechanics. It is known as Schrödinger's cat, and even if you have never studied physics, there is a good chance you have heard the name. It appears in television shows, novels, internet jokes, cartoons, and conversations where someone wants to describe a situation that seems undecided. The usual version is simple enough. A cat is placed inside a sealed box. Something inside the box may kill it. Until we open the box, we are told that the cat is somehow both alive and dead. Then someone looks, the uncertainty disappears, and the cat becomes one thing or the other. It is memorable. It is strange. It is also very easy to misunderstand. Before we go any further, I would like to know where you are listening from tonight and whether Schrödinger's cat is already familiar to you. Perhaps you have heard the phrase many times but have never really known what it was supposed to demonstrate. Perhaps you understand the basic idea but have always wondered whether physicists genuinely believe that a real cat could somehow be alive and dead at once. Or perhaps this is your first encounter with the experiment and you're already wondering why anyone thought quantum physics needed a cat in the first place. If you enjoy these slow explorations through physics, where we can take complicated ideas and examine them without turning them into a race, you can like the video and subscribe to Physics with William. It helps this quiet little corner of science reach other curious people who may also enjoy falling asleep while somebody explains why reality refuses to behave itself. For now, make yourself comfortable and let us begin with the box. The strange thing about Schrödinger's cat is that the cat was never really the point. It was not designed as a serious proposal for an experiment involving an unfortunate animal. Schrödinger was not suggesting that physicists should build such a device, place a cat inside it, and then stand around discussing philosophy while the cat developed a very reasonable dislike of scientists. The entire setup was imaginary. It was created to expose a problem. More specifically, it was created to show how peculiar some ideas in quantum mechanics appeared when they were extended from tiny particles to ordinary objects. To understand why this mattered, we need to remember what physics looked like before quantum mechanics arrived. For a long time, the universe seemed to follow rules that were difficult perhaps, but understandable in principle. A stone had a location, a planet followed an orbit, a pendulum swung along a path, a moving object had a speed and a direction. If you knew enough about the forces acting on something and enough about its starting condition, then in principle you could work out what it would do next. You might not have all the information, your measurements might be imperfect, the calculations might be unpleasant enough to ruin an otherwise peaceful afternoon. But the basic picture was reassuring. Objects had definite properties whether anyone was looking at them or not. If you placed a football inside a cupboard and closed the door, you would not normally imagine that the football had entered some mysterious state because you could no longer see it. It would still be somewhere inside the cupboard. Perhaps on the left, perhaps on the right, perhaps wedged behind the vacuum cleaner where nobody will find it until next spring. Your lack of knowledge does not make the football uncertain in itself. It simply means you do not know its position. The same applies to a playing card turned face down on a table. It already has a value. You may not know whether it is a queen or a 7, but lifting the card reveals the answer. The act of looking does not normally create the value printed on it. This ordinary way of thinking became much more difficult when scientists began investigating atoms, electrons, light, and the other tiny ingredients of matter. Experiments revealed behavior that did not fit comfortably into the familiar picture. Light could behave in ways associated with waves and in ways associated with particles. Electrons could produce patterns that suggested several possible routes were somehow involved in what eventually happened. The theory that emerged from these discoveries became quantum mechanics, and it worked with extraordinary accuracy. It predicted experimental results better and better as the theory developed. The difficulty was not that quantum mechanics failed. The difficulty was that it succeeded while describing nature in a way that seemed deeply unlike everyday experience. One of the ideas at the centre of this new theory was superposition. We will spend much more time with that idea later, but for now it is enough to understand the basic problem it creates. In certain situations, a quantum system is not described as having one ordinary definite state that we simply happen not to know. Instead, the theory represents several possibilities together. Those possibilities can influence the results of experiments in ways that ordinary hidden uncertainty cannot easily reproduce. Then a measurement occurs, and we obtain one definite outcome. That change is where the trouble begins. Imagine a tiny radioactive atom. Radioactive atoms are unstable, which means they can decay. We can often predict the probability that decay will happen within a certain period, but we cannot treat the individual event exactly like the movement of a classical clockwork mechanism. According to the quantum description, before the decay is detected, the system may involve a combination of the possibility that the atom has decayed and the possibility that it has not. For a microscopic object, this already sounds strange, but perhaps not unbearably strange. Atoms are tiny. Nobody has held one in their hand. Nobody has watched an individual atom behave while making breakfast. We are prepared to accept that the atomic world may not follow our everyday instincts. This is where Schrödinger did something clever. Instead of leaving the problem at the level of an atom, he connected the atom to something large and familiar. He imagined a sealed box containing a cat, a small radioactive source, a detector, and a mechanism capable of releasing a deadly substance. If the radioactive atom decays, the detector notices. The detector then activates the mechanism. The substance is released, and the cat dies. If the atom does not decay, the detector remains silent, the mechanism does nothing, and the cat stays alive. The important detail is that the fate of the cat has now been connected directly to a quantum event. Suppose we close the box and wait. From outside, we cannot see whether the atom has decayed. We cannot see whether the detector is activated. We cannot see whether the cat is alive. In ordinary reasoning, this does not seem especially mysterious. Either the atom decayed or it did not. Either the mechanism activated or it did not. Either the cat is alive or it is dead. We simply do not know which situation exists until we open the box. That would make the whole experiment no more mysterious than checking whether someone has eaten the last biscuit. But Schrödinger was pointing at a deeper issue. If the radioactive atom is described quantum mechanically as involving more than one possible state, and the atom is connected to the detector, and the detector is connected to the mechanism, and the mechanism determines whether the cat survives, then where does the quantum description stop? Does it stop at the atom? Why there? The detector is made of atoms too. Does it stop at the detector? Why should it? The mechanism is also physical matter. What about the poison? What about the cat itself? If every link in the chain is part of the same physical process, then the logic of the quantum description seems to spread outward. A possibility in the atom becomes associated with a possibility in the detector. The detector becomes associated with two possible states of the mechanism. Those possibilities become associated with two possible conditions of the cat. One possibility contains a living cat, the other contains a dead cat. Now the quantum strangeness has escaped the microscopic world. This is exactly what Schrödinger wanted us to notice. He was not telling everyone to calmly accept that ordinary cats are literally alive and dead whenever nobody can see them. He was showing that if certain ways of talking about quantum states were applied, without carefully explaining where measurement enters the story, they seem to produce a ridiculous result. The cat is therefore less like a discovery, and more like an objection. It is Schrödinger asking, in effect, whether we are really comfortable carrying this description all the way from a radioactive atom to a living creature. The brilliance of the example is that it removes our ability to hide behind the unfamiliarity of the microscopic world. If someone tells you that an electron is in a strange combination of possibilities, you may simply accept it because electrons are already mysterious. They are very small, they behave according to rules most of us do not encounter directly. But if someone says your cat is in two radically different conditions until you look at it, your instincts begin protesting almost immediately. A cat seems definite. A cat is not a vague mathematical possibility wandering around the kitchen. It is either asleep on the sofa or pretending not to hear you. It is either waiting beside an empty food bowl or behaving as though nobody has fed it for several years, despite having eaten 12 minutes ago. Cats have many mysterious qualities, but from our ordinary experience, indefinite existence is not generally one of them. That is why Schrödinger chose a cat. The animal turns a technical question into something impossible to ignore. The question is not really whether cats are strange. The question is what counts as a measurement in quantum physics, and how one definite outcome appears from a description containing several possibilities. This sounds like a small technical detail until you try to answer it. Suppose we say the quantum possibilities remain until a measurement happens. Fine. What exactly is a measurement? Is it when the atom interacts with the detector? If so, perhaps the story stops there. The detector records whether decay occurred, and the cat simply experiences the consequence. But why should the detector be special? It is just another physical object. Perhaps measurement happens when the result becomes large enough to see. But how large is large enough? There is no obvious sign in nature saying that objects below a certain size must obey quantum mechanics, while objects above it may return to normal behavior. Perhaps measurement occurs when a human being looks. That creates another problem. Why should a human observer have a unique role? Imagine placing a camera beside the box. The camera records the inside, but nobody watches the recording for a week. Did the result become definite when the camera recorded it, or only when someone watched the video? What if the camera sends the recording to a computer? What if the computer analyzes it, but no person reads the result? What if a dog looks into the box? What if the cat itself is aware of what happened? The questions become uncomfortable very quickly. This is why casual phrases such as observation creates reality can cause more confusion than they solve. In physics, observation usually means some kind of physical interaction that allows information to become correlated with a measuring device or environment. It does not necessarily mean that a human mind stares at something intensely until the universe makes a decision. And yet the role of measurement was genuinely difficult to understand in the early development of quantum mechanics. Even today, physicists and philosophers disagree about the best interpretation of what the theory says is actually happening. That disagreement is one reason the cat remains famous. It sits exactly at the point where the mathematics of quantum theory meets the world we experience. On one side of the box are microscopic possibilities, on the other side are definite events. Inside the box is the problem of explaining how those descriptions fit together. The cat also helps us separate two very different kinds of uncertainty. This distinction is essential. Imagine I place a coin inside a small box, shake it, and put the box on the table without opening it. You do not know whether the coin shows heads or tails. You might say there is a chance of heads and a chance of tails, but you assume that the coin has already landed. There is a definite answer inside. Your ignorance is not a property of the coin, it is a property of you. Quantum superposition cannot always be understood in that simple way. The possible outcomes in a quantum state can interfere with one another. Experiments can detect consequences of the relationship between those alternatives. That means the theory is doing something more than describing our lack of knowledge about an ordinary hidden condition. This is where the cat becomes much more than a closed box with an unknown answer. If it were merely an unknown answer, there would be no quantum mystery at all. You could replace the radioactive atom with a coin toss, close the box and say, the cat's fate depends on whether the coin lands heads or tails. Before looking, you would not know whether the cat survived. Nobody would call that quantum mechanics. It would simply be a rather unpleasant game of chance. Schrödinger needed the radioactive atom because the atom brings genuine quantum behavior into the story. The detector then amplifies that microscopic event. This amplification matters enormously. Every real measuring instrument in quantum physics must take something tiny and turn it into something we can record. A single microscopic interaction has to become a click, a flash, a mark, an electrical signal, or some other visible event. The cat is an absurdly dramatic version of that amplification. Instead of a small pointer moving, an entire living animal changes condition. This forces us to confront the boundary between quantum possibility and macroscopic fact. Where is that boundary? For many years, one common attitude was that quantum mechanics describes microscopic systems, while measuring devices are treated classically. That approach works extremely well for calculating experimental results. The physicist prepares a quantum system, allows it to evolve, measures it with an apparatus, and records an outcome. Operationally, there is often no problem. The deeper question is whether that division describes reality or merely provides a convenient method for doing experiments. After all, the measuring device is made from atoms, the laboratory is made from atoms, the physicist is made from atoms, the notebook is made from atoms. The cup of tea beside the notebook is made from atoms, and depending on how long the discussion continues, may eventually become an example of thermodynamics as well. If the underlying ingredients obey quantum mechanics, why should large collections of those ingredients suddenly behave according to completely different rules? Modern physics has developed powerful tools for understanding part of this transition. One of the most important is decoherence, which describes how quantum systems interact with their surroundings. A tiny isolated system can preserve delicate relationships between different quantum possibilities. A large object cannot normally remain isolated in the same way. It interacts constantly with air molecules, light, heat, vibrations, nearby matter, and its own enormous number of internal components. A living cat is an especially terrible candidate for isolation. It is warm, it breathes, its body contains countless chemical reactions. It exchanges energy with its environment. Every moment, information about its physical condition becomes connected with an enormous number of surrounding particles. This environmental interaction destroys the sort of clean interference that makes isolated quantum superpositions noticeable. That helps explain why we do not walk through a world filled with visibly superposed furniture, animals, and breakfast items. Your chair does not seem to be in several places at once. Your coffee cup does not remain simultaneously full and empty until you check it. Your cat does not appear as a fuzzy combination of sitting on the bed and knocking something expensive onto the floor. At ordinary scales, the environment makes quantum alternatives behave very differently from carefully isolated microscopic states. But even this does not automatically answer every question raised by Schrödinger. Decoherence can explain why alternatives stop interfering in the familiar way, and why the classical world emerges so effectively from quantum physics. What it does not settle by itself is why an observer experiences one particular result. That remaining puzzle opens the door to different interpretations. Some interpretations say that the quantum state undergoes a real collapse when measurement occurs. One possibility becomes actual, and the others disappear from the physical description. Other interpretations say there is no collapse at all. The mathematics continues smoothly, and what we call different outcomes belong to different branches of a larger quantum reality. Still others argue that quantum theory is fundamentally about information, relationships, or the probabilities of observations rather than a literal picture of what exists between measurements. Each approach tries to make sense of the same successful experimental framework. The disagreement is not about whether quantum mechanics works, it works extremely well. The disagreement is about what the successful mathematics means. This may sound like philosophy wearing a laboratory coat, and in some ways it is. But the distinction matters because physics has always tried to do more than provide numbers. Scientists also want to understand what kind of world could produce those numbers. Schrödinger's cat became famous because it compresses that entire debate into a single image, a box, a random quantum event, a mechanism, a cat, an observer outside. Nothing about the arrangement is mathematically complicated in principle, but the conceptual problem is enormous. What should we say exists before the box is opened? If we answer that the cat is simply alive or dead and we merely do not know which, then we need to explain what happened to the quantum superposition that began the process. If we answer that the entire arrangement remains in a superposition, then we seem committed to talking about a living and dead cat together in the quantum description. If we say the superposition collapses somewhere along the chain, then we need to say where and why. And if we say there is no collapse, then we need another explanation for why we experience only one outcome. The cat is therefore not an answer to quantum mechanics, it is a question disguised as an animal. That is probably the single most important thing to understand before going deeper. Popular culture often treats Schrödinger's cat as if it means something remains undecided until you check it. That is only the surface. The deeper issue is whether quantum mechanics describes reality itself as containing multiple alternatives before measurement, and how those alternatives give rise to the single definite world we experience. Schrödinger wanted the cat to expose the tension. He was not celebrating it. In fact, the entire setup was designed to make the interpretation look unreasonable when applied to ordinary objects. That historical context changes the tone of the thought experiment completely. Instead of imagining Schrödinger smiling proudly and announcing that he had discovered a cat that was both alive and dead, picture a physicist pointing at the consequences of an idea and asking whether everyone was really prepared to accept them, and that question has never entirely gone away. Experiments have become more sophisticated. Quantum theory has become the foundation of enormous areas of modern science and technology. We use quantum principles to understand chemistry, semiconductors, lasers, magnetic resonance imaging, atomic clocks, and the developing field of quantum computing. The theory is not an eccentric curiosity. It is one of the most thoroughly tested frameworks in science. Yet the simple question behind the cat remains difficult. What exactly is happening before a measurement produces its result? That question becomes even stranger when we realize that superposition is not merely a philosophical label, it produces experimental effects. Under carefully controlled conditions, quantum alternatives can interfere. Scientists can manipulate those possibilities and use them. Quantum computers, for example, are being developed partly because quantum states can encode and manipulate information in ways that have no straightforward classical equivalent. Maintaining those states is extremely difficult because interaction with the environment causes decoherence. In other words, the delicate quantum behavior hiding behind Schrödinger's cat is something laboratories now work very hard to preserve. The irony would probably have amused Schrödinger. A thought experiment intended to reveal how strange quantum ideas became when extended toward large systems now sits in a world where scientists deliberately try to create larger and better controlled quantum systems. We have not put a cat into the required kind of superposition, nor is anyone planning to do so, but we have pushed quantum behavior into increasingly complex physical systems. That makes the boundary between quantum and classical feel less like a solid wall and more like something that emerges gradually through interaction, complexity, and environmental noise. The box therefore contains more than a cat. It contains a disagreement about what a physical state is. It contains a question about measurement. It contains the problem of how microscopic uncertainty becomes macroscopic fact. It contains the reason physicists still argue about interpretations nearly a century after quantum mechanics took its modern form. And strangely enough, the cat itself may be the least mysterious thing in there. Once the box is closed, the real difficulty begins before anyone touches the lid. To see why, we need to stop thinking of superposition as simply not knowing which answer is correct, and look more carefully at what the quantum description is actually doing before a measurement occurs. That is where the familiar picture of a hidden coin stops working, where several possibilities begin to influence one another, and where the strange logic behind Schrödinger's cat starts to become much clearer. To understand what is waiting inside that closed box, we need to look more carefully at the idea that makes the whole thought experiment possible in the first place. Superposition is often introduced with a sentence that sounds wonderfully simple. A quantum object can exist in more than one state at the same time. That sentence is not completely wrong, but it is incomplete enough to cause trouble almost immediately. It can make superposition sound like an ordinary object that happens to be undecided, as though an electron were a coin spinning in the air, and quantum mechanics simply refuse to tell us whether it would eventually land on heads or tails. The real idea is stranger than that, because the different possibilities in a quantum superposition are not merely possibilities in our minds. Under the right conditions, they can influence one another. They can combine, reinforce, cancel, and produce patterns that would not appear if the system had secretly chosen one ordinary state all along. This is the point where quantum uncertainty separates itself from the familiar uncertainty of everyday life, and it is also the point where Schrödinger's cat stops being a joke about not knowing what is inside a box and becomes a genuine problem about what physical reality is doing before the box is opened. Suppose you walk into a kitchen and notice a closed cupboard. Somewhere inside that cupboard is a mug. You do not know whether the mug is on the top shelf or the bottom shelf. Perhaps someone moved it. Perhaps it is hiding behind a saucepan. Perhaps, as often seems to happen with useful household objects, it has migrated to the one place nobody would logically put it. From your point of view, several possibilities exist. The mug could be here or there, but nobody would normally say the mug itself is in a physical combination of those locations. You assume there is already one correct answer. Your uncertainty belongs to you. Open the cupboard and you simply discover which possibility was true all along. The same reasoning works with a letter in a sealed envelope, a card face down on a table, or a cat hiding somewhere in the house. You may not know where the cat is, but the cat probably knows perfectly well, and is likely using that knowledge to sit somewhere inconvenient. Quantum mechanics asks us to be much more careful. In some experiments, treating a quantum system as though it secretly possessed one ordinary definite state before measurement does not reproduce what we observe. The possibilities are not just a list of our guesses. Their relationship matters physically. This is easiest to see through interference, because interference gives us evidence that alternatives in the quantum description can affect the final outcome. To get a feeling for this, it helps to begin with ordinary waves. Imagine gentle ripples travelling across the surface of a pond. When two ripples meet, they overlap. In some places, the peaks line up and the resulting wave becomes larger. In other places, a peak meets a trough and the two partly cancel. If many waves pass through two narrow openings and spread outward, their overlapping patterns can create alternating regions where the motion is stronger and weaker. Nothing especially mysterious is happening. Waves naturally occupy extended regions, and when they overlap, their shapes combine. Light can produce this kind of interference. For centuries, this was one of the strongest pieces of evidence that light had wave-like behaviour. Shine light through two narrow openings under the right conditions, and instead of simply seeing two bright patches directly behind the openings, you can observe a pattern of brighter and darker regions. The waves travelling through one opening overlap with the waves travelling through the other. In some places they strengthen one another, in others they weaken one another. So far this is familiar wave behaviour. Then quantum physics makes the situation uncomfortable by allowing the light to arrive in individual packets. If the light is made extremely faint, the detector can register separate events one at a time. A single event appears at one location, then another appears somewhere else. At first the pattern seems scattered and random, but after many events the same interference structure gradually emerges. Individual arrivals accumulate into a pattern that depends on both paths being available. Electrons can do something similar. An electron reaches the detector at a particular location, yet many electrons sent through the experiment one at a time can build an interference pattern. This is where the ordinary picture begins to fail. If each electron simply chose one opening and travelled through it like a tiny grain of sand, we would expect the final distribution to look like a mixture of two ordinary alternatives. Instead, When the experiment preserves the required quantum conditions, the possibilities associated with the two paths interfere. Even when only one electron is moving through the apparatus at a time, the eventual statistics show the signature of that interference. It is tempting at this point to ask which opening the electron really used. That seems like a perfectly reasonable question. If something travelled from one side of the experiment to the other, surely it must have gone somewhere. So we arrange a detector that tells us which path the electron took. Now something important happens. Once reliable information about the path is created, the interference pattern disappears. We obtain results consistent with distinguishable alternatives instead. This is not because the electron became shy when it noticed a physicist watching. It is not because human curiosity frightened the wave away. Measuring the path requires a physical interaction, and that interaction changes the quantum situation. Information about the alternatives becomes connected with the measuring apparatus or the surrounding environment. The delicate relationship that allowed the paths to interfere is lost. This distinction is extremely important because popular discussions of quantum mechanics often turn measurement into a mysterious act of consciousness. Someone looks, and reality suddenly changes because a mind has noticed it. That idea has appeared in many philosophical discussions, but it is not necessary for understanding the basic experimental effect. A detector does not need to be conscious. A machine does not need opinions about quantum mechanics. Physical interaction can be enough to destroy the conditions required for observable interference. The question of what ultimately counts as a measurement remains subtle, but it is better to begin with physics rather than imagination. Quantum systems interact with other systems. Those interactions create correlations. Information about different alternatives can spread into the environment. Once that happens, the clean superposition we hope to preserve becomes much more difficult to observe. So what exactly is superposition describing? At the simplest level, it tells us that a quantum state can contain several possible measurement outcomes together in a structured way. The structure matters because those possibilities can interfere. If it were merely ordinary ignorance, there would be no interference between them. Imagine again that a coin has been hidden under a cup. You do not know whether it is heads or tails. Suppose there are equal chances from your point of view. Nothing you do with another hidden coin will create a pattern in which the heads possibility of the first coin cancels the tails possibility. The possibilities exist only in your description because you lack information. With quantum systems, alternatives can combine in ways that influence observable probabilities. That makes the uncertainty fundamentally different from a simple lack of knowledge. This is also why phrases such as both states at once should be treated carefully. They are useful because they remind us that the quantum description includes more than one alternative, but they can also encourage an image in which a particle is literally doing two ordinary classical things simultaneously. Quantum mechanics is not simply classical reality multiplied. The alternatives belong to a quantum state, whose behaviour follows rules unlike those of ordinary objects. When we measure, we obtain a definite result. Between preparation and measurement, the state evolves in a way that can preserve relationships between possible outcomes. Those relationships are what allow interference. Saying both at once is therefore a shortcut, not a complete picture. Consider another simple example. Imagine a quantum particle with a property that can produce one of two outcomes when measured in a particular way. Before the measurement, we can prepare the particle in a superposition associated with those two possibilities. Measure it, and the apparatus records one definite result. Prepare another identically and repeat the process, and perhaps the other result appears. Continue many times, and a stable statistical pattern develops. Quantum mechanics can predict that pattern with remarkable accuracy. But if you ask which result was already definitely present before the measurement, the theory does not always allow you to answer in the ordinary classical way. Change how you choose to measure the system, and the set of meaningful possibilities can change as well. This was deeply unsettling to physicists who had grown accustomed to imagining that physical objects carried definite properties around with them, whether or not anyone happened to check. One reaction is to suppose that perhaps the missing definite properties are simply hidden. Maybe quantum mechanics is incomplete. Maybe particles really do possess exact values and instructions, but we cannot see them. This possibility was taken seriously, and versions of it remain part of discussions about the foundations of quantum physics. The difficulty is that experiments have placed strong restrictions on what such hidden descriptions can look like. The simplest picture, in which each particle quietly carries a complete set of ordinary local instructions determining every possible measurement outcome, does not reproduce the full behavior observed in quantum experiments. Nature does not seem willing to become classical simply because classical pictures feel more comfortable. Superposition, therefore, is not merely a word physicists invented because they enjoy making simple things difficult. It is built into the predictive structure of quantum theory. It is also something experimentalists deliberately create, preserve, and manipulate. Modern laboratories routinely work with quantum states where maintaining coherent alternatives is essential. The word coherent matters here. A superposition is useful when the different parts of the quantum state preserve the relationships that allow interference. Once uncontrolled interactions spread information into the environment, those relationships become inaccessible, and the observable quantum behavior begins to resemble an ordinary mixture of alternatives. This brings us closer to the box, because Schrödinger's thought experiment depends on extending that quantum description outward. Begin with a radioactive system. For a chosen period of time, quantum mechanics may describe a possibility of decay and a possibility of no decay. If the system remains part of an isolated quantum description, those alternatives are represented together. Then connect the atom to a detector. If the atom decays, the detector changes. If it does not, the detector remains in another condition. The detector has now become correlated with the radioactive system. One alternative involves decay and detector activation. The other involves no decay and no activation. Nothing requires us to stop there. Connect the detector to another device. The combined description spreads again. One alternative contains an activated detector and a triggered mechanism. The other contains an inactive detector and an untouched mechanism. Place a cat at the end of that chain, and the difference becomes biological. In one alternative, the chain ends with the cat dead. In the other, it ends with the cat alive. The mathematical logic that seems strange but tolerable for one atom has now been connected to something unmistakably large. This is what makes the thought experiment so effective. It is not necessary to believe that a real cat can be maintained in a clean superposition of life and death in an ordinary box. In practice, a cat is one of the least isolated systems imaginable. It contains an enormous number of particles. It is warm. It breathes. Molecules move through it. Heat radiates away. Light and air interact with its body. Every internal process creates countless opportunities for information to become distributed into the surroundings. Any delicate coherence between macroscopically different conditions would be destroyed with extraordinary speed. The environment would become entangled with the alternatives long before a human observer decided to open the lid. Yet saying that does not make Schrödinger's question disappear. It changes the form of the question. If environmental interaction causes the alternatives to lose observable coherence, does that explain why one definite outcome occurs, or does it only explain why the alternatives can no longer interfere in a way we can easily detect? That difference sits at the heart of later discussions about decoherence and interpretation. For now, it is enough to notice that the problem is not solved by saying large things behave classically. We want to know why they behave classically when large things are built entirely from smaller components that obey quantum rules. You can see the tension by imagining a chain of increasingly complicated objects. Start with one electron. Quantum behavior seems perfectly acceptable. Add several atoms, still quantum. Combine atoms into a molecule. Quantum effects can still be observed under suitable conditions. Make the molecule larger. The experiment becomes harder, but there is no obvious moment when nature announces that quantum mechanics has expired. Build larger structures and interaction with the environment becomes increasingly difficult to control. classical behaviour emerges more strongly, but the change looks more like a loss of isolation than a sudden change in the fundamental laws. This is why scientists have spent so much effort creating extremely controlled environments. They cool systems, shield them, remove air, reduce unwanted vibrations, and protect delicate quantum states from surrounding noise. Quantum computers face exactly this problem. Their useful quantum states are fragile because uncontrolled interactions with the environment produce decoherence. Engineers do not worry that a computer user will accidentally look at a quantum bit too intensely. They worry about physical noise, thermal effects, stray fields, imperfect control, and all the other ways the outside world can become correlated with the system. The success of these experiments tells us something important about superposition. It is not merely philosophical decoration placed on top of quantum mechanics. If coherent superpositions could not be created and manipulated, much of quantum technology would make no sense. At the same time, the difficulty of preserving them helps explain why everyday life looks so different. The quantum world is not hidden because it only exists in special mystical locations. It is hidden because the large-scale environment is extremely effective at spreading quantum information and destroying accessible coherence. Suppose you tried to create an obvious superposition involving an ordinary object. Perhaps a tiny mirror could be arranged so that a quantum process is associated with two slightly different motions. To preserve the effect, you would need to prevent the surrounding world from learning too much about which motion occurred. A stray particle of light bouncing from the mirror could carry information away. A collision with a molecule could do the same. Heat inside the object could couple different parts together. The larger and warmer the system becomes, the harder the task becomes. Now replace the mirror with a living cat. The challenge stops being merely difficult and becomes ridiculous. The cat itself is practically an environment containing several more environments, all of them busy. This practical fact is sometimes mistaken for the entire message of Schrödinger's thought experiment. Someone hears about decoherence and concludes that the cat problem has simply vanished. But Schrödinger's concern was more foundational. He was asking what the quantum state represents, and how the formal description relates to definite macroscopic reality. Decoherence tells us why interference between large-scale alternatives becomes effectively unavailable. It explains an enormous amount about the emergence of classical behavior. But if the complete quantum description still contains correlated alternatives, an interpretation must tell us what we should think those alternatives mean. One possibility is that only one outcome becomes real when a measurement occurs. This is the language of collapse. The quantum state begins with several possible outcomes and then changes to the one that has been observed. This is often how students first learn to use quantum mechanics, because it gives clear instructions. Prepare the state, allow it to evolve, measure, obtain an outcome according to the predicted probabilities, update the state. For laboratory calculations, this can work beautifully. The trouble begins when we ask exactly when collapse occurs. Does the radioactive atom collapse when it interacts with the detector? Does the detector collapse when it triggers the mechanism? Does the cat somehow complete the measurement? Does the person outside the box matter? If the boundary between quantum system and classical measuring device is merely practical, then the fundamental story remains unclear. This was one reason Schrödinger found the situation unsatisfactory. Another possibility is to deny that collapse happens at all. In that case, the quantum state continues evolving according to the same underlying rules, and the different possible outcomes remain within the larger description. This creates interpretations in which observers become associated with different branches of the result. From the perspective of each observer, one outcome is experienced. The other alternatives have not been physically erased. They belong to other branches that no longer interfere in any practical way. This kind of interpretation solves one problem by accepting something many people find even stranger. There are other approaches as well. Some introduce additional physical processes that cause collapse for sufficiently large systems. Some describe quantum states more as tools for assigning probabilities to experiences or information. Some treat properties as relational, meaning they are defined relative to interactions between systems rather than existing as one absolute list for everything. Some search for deeper underlying variables. Quantum theory has inspired no shortage of attempts to explain what exactly the mathematics is saying, which is what tends to happen when a theory is extremely successful and philosophically irritating at the same time. Before choosing among any of those possibilities, however, it is useful to stay with superposition itself and remove one more common misunderstanding. A superposition does not mean that every imaginable possibility exists. Quantum mechanics is not a permission slip for anything whatsoever to happen. If a particle is prepared in a particular state, only certain outcomes may be relevant to a chosen measurement, and their probabilities are constrained very precisely. You cannot invoke superposition to claim that your missing keys are simultaneously in the kitchen, on the moon, inside a whale, and attending a conference in Vienna. Quantum theory is strange, but it is not careless. Nor does superposition mean that uncertainty automatically appears whenever we refuse to look at something. Closing your eyes does not turn your bedroom into a quantum experiment. The objects around you are constantly interacting with the environment. Light, air, heat, and matter are continuously carrying information about them. A macroscopic object does not need a conscious observer to become effectively classical. The world is already watching itself through interaction. That idea makes the sealed box much more interesting. The box is not magical because it blocks your view. A normal sealed box still contains air, heat, the detector, the mechanism, the cat, and countless internal interactions. The reason Schrödinger closed the box was conceptual. It prevents the external observer from knowing the outcome, and forces us to ask how the quantum description should be handled before that observer receives the information. The box creates a clean separation in the story, even though a real physical box would not isolate the system perfectly from all environmental interactions. The observer outside therefore becomes part of the puzzle, but not because human vision has some special beam that collapses reality. The observer represents the point at which a definite result enters ordinary experience. Open the lid, and you do not report seeing a vague mixture of living and dead. You report one condition. The question is, why the quantum description that began with alternatives produces an experience containing one result. By the time Schrödinger proposed his cat in 1935, this issue was already part of a larger disagreement among the founders of quantum mechanics. They were not arguing because they lacked successful mathematics. They were arguing because the mathematics was successful enough that they could no longer dismiss the strange implications. Some physicists believed asking what happened between measurements was unnecessary or even misguided. Physics should predict what experiments reveal, and quantum mechanics did that exceptionally well. Others, including Schrödinger and Einstein, were uncomfortable with the idea that a theory could give precise probabilities without offering a clearer account of the underlying physical reality. That disagreement is what gave the cat its purpose. Schrödinger wanted to take the language used for microscopic systems and amplify it until nobody could pretend the conceptual problem was harmless. If a radioactive atom could be represented through alternatives, and if quantum mechanics applied universally, then the measuring device had to be included too. If the device was included, the cat followed. The cat was not an arbitrary flourish. It was the point at which the interpretation became impossible to ignore. This is also why Schrödinger's cat remains useful, even though our understanding of quantum systems has advanced enormously. The details of how we discuss measurement have become more sophisticated. Decoherence has given us a much better account of why large-scale interference disappears. Experiments have tested quantum behavior in systems far beyond what early physicists could manipulate. Yet the cat still asks a simple question. What does the quantum state mean before a definite outcome is experienced? Superposition puts that question on the table because it refuses to behave like ordinary ignorance. The possibilities have structure. Their relationships have observable consequences. They can interfere while coherence is preserved. Once interaction with the environment spreads information about them, interference fades and classical behaviour emerges. Then measurement gives us a definite record. Every part of that sequence can be described mathematically with a success, but the interpretation of what is physically happening remains more complicated than the simple phrase "both at once" suggests. And this is where we begin to see why Schrödinger did not introduce the cat because he wanted everyone to admire how wonderfully strange quantum mechanics was. He introduced it because he thought the strange result revealed a weakness in the way the theory was being interpreted. The cat was meant to make people uncomfortable. It was meant to take a microscopic idea that sounded manageable and push it into the ordinary world until the consequences became difficult to accept. To understand exactly what he was objecting to, and why one of the founders of quantum mechanics chose such an exaggerated example, we need to look at the argument Schrödinger was having with the other architects of the quantum world, and at the problem he believed his unfortunate imaginary cat had exposed. By the middle of the 1930s, quantum mechanics had already achieved something unusual. It had become enormously successful before anyone had fully agreed on what it meant. Physicists could use it to predict the behaviour of atoms, explain the structure of matter, and understand processes that classical physics simply could not handle. The calculations worked, the experiments agreed, new discoveries kept arriving, yet underneath that success sat a question that refused to go away. Was quantum mechanics describing reality itself, or was it only telling us what we should expect to observe when we perform an experiment? That distinction may sound philosophical, but for Erwin Schrödinger it was serious enough to inspire one of the most famous imaginary animals in science. Schrödinger was not an outsider criticizing a theory he did not understand. He was one of the people who had helped create quantum mechanics. His work provided one of the central mathematical descriptions used to follow how quantum systems change. He understood better than almost anyone how powerful the theory was, and that was precisely why his discomfort mattered. He was not objecting because quantum mechanics gave poor predictions. He was objecting because some interpretations seemed to ask physicists to accept a description of reality that became increasingly difficult to understand when extended beyond tiny particles. The debate that eventually produced the cat involved several of the most important physicists of the 20th century. Albert Einstein was deeply uneasy with the idea that quantum mechanics, as it was commonly interpreted, gave a complete account of physical reality. Niels Bohr was much more comfortable with the theory's emphasis on measurements and experimental arrangements. Werner Heisenberg had helped develop the mathematical framework and argued that certain classical ideas could not simply be carried into the quantum world unchanged. Schrödinger shared some of Einstein's discomfort, although he approached the problem in his own way. They were not arguing about whether quantum mechanics produced useful results. Everyone involved knew that it did. The disagreement was about what those results allowed us to say about what actually existed before a measurement was made. Einstein had a strong preference for a world in which physical systems possessed properties independently of whether someone happened to measure them. If an object was somewhere, it was somewhere. If something happened, it happened. Our knowledge might be incomplete, but reality itself should not depend on our decision to observe it. Quantum mechanics seemed to challenge that expectation. In many situations, the theory did not assign one definite value to a property before measurement. It provided a structured set of possibilities and the probabilities associated with different outcomes. To some physicists, this was not a defect. It was simply how nature worked. Asking what value existed before measurement could be like asking for the exact edge of a cloud. Perhaps the question itself assumed a kind of reality that quantum systems did not possess. Bohr in particular emphasized that the outcome of a quantum experiment could not always be separated from the way the experiment was arranged. The measurement was not merely a passive inspection of an independently existing classical property. The whole experimental context mattered. Einstein was not satisfied. Neither was Schrödinger. Their concern became sharper in 1935 when Einstein, together with Boris Podolsky and Nathan Rosen, published an argument that challenged the completeness of quantum mechanics. Their reasoning involved two particles prepared in a connected quantum state. According to the theory, measurements performed on the particles could show correlations that seemed deeply strange if the particles were far apart. The argument was carefully designed to suggest that quantum mechanics might not contain the full description of physical reality. The details of that argument can become technical, but its spirit is straightforward. Einstein and his collaborators wanted to show that if quantum mechanics allowed you to predict a property of a distant system without physically disturbing it, then perhaps that property must have had some definite reality all along. If the theory did not include that definite value before measurement, then perhaps the theory was incomplete. This was part of Einstein's broader discomfort with a universe described fundamentally through probabilities. He did not object to probability when it represented ignorance. If you toss a coin, you may not know the result in advance because you do not know every detail of its motion. That is perfectly ordinary. The coin itself still follows a definite physical path. Einstein hoped something similar might eventually be discovered beneath quantum mechanics. Perhaps the probabilities were telling us that our description was incomplete rather than that nature itself lacked definite properties. Bohr responded strongly to Einstein's argument. He believed the challenge relied too heavily on classical ideas that could not simply be imported into quantum physics. In Bohr's view, the meaning of a physical quantity depended on the experimental conditions used to measure it. It was not always sensible to imagine that every possible property existed with a definite value before we decided what kind of measurement to perform. Schrödinger followed this exchange closely. In fact, the Einstein argument inspired him to think more deeply about the strange relationships quantum mechanics allowed between separated systems. Around this period, he introduced the term entanglement to describe a situation where parts of a quantum system could no longer be given independent descriptions in the ordinary way. What happened to one part was connected to the description of another. Schrödinger considered entanglement not a minor curiosity, but one of the defining features of quantum theory. It meant that once systems interacted, the quantum description could spread across them. You could no longer always speak about each piece separately. The state belonged to the combined system. That idea is exactly what makes the cat experiment work. Begin with a radioactive atom. On its own, the atom has a quantum description involving the possibility of decay and the possibility of no decay during a chosen interval. Connect the atom to a detector and the combined system becomes correlated. Decay is associated with one detector condition. No decay is associated with another. Connect the detector to a mechanical device and the correlations spread again. One chain contains a triggered mechanism, the other does not. Schrödinger's crucial move was refusing to stop the logic just because the objects were becoming larger. If quantum mechanics is a universal physical theory, why should the detector suddenly receive special treatment? The detector is made from matter. The mechanism is made from matter. The cat is made from matter. All of that matter ultimately consists of the same kinds of quantum ingredients that the theory is supposed to describe. So Schrödinger pushed the description outward until it reached something that nobody could comfortably call vague, a living cat or a dead cat. The setup was deliberately extreme. Schrödinger wanted the consequences to sound unreasonable. If he had chosen two slightly different positions of a tiny pointer, people could have shrugged and continued arguing. A cat made the problem impossible to ignore. Imagine the entire sequence once more. A radioactive event may occur. A detector responds if it does. A mechanism releases poison if the detector is triggered. The cat's survival depends entirely on that chain. The box is closed so that an observer outside does not know which result has occurred. If the quantum state remains a superposition all the way through the physical interactions, then the description does not stop with the atom. It becomes a combined state involving the atom, the detector, the mechanism, and eventually the cat. This was the absurdity Schrödinger wanted to expose. He was not proposing that we should celebrate the conclusion by saying, "Wonderful, the cat is alive and dead at the same time." His point was closer to the opposite. If an interpretation leads us to say something this strange about an ordinary animal, perhaps we should examine the interpretation more carefully. The cat was therefore a criticism of an overly simple reading of quantum measurement. That historical point is easy to miss because the thought experiment has become so famous that its original purpose has almost been reversed. Today, people often introduce Schrödinger's cat as evidence of how wonderfully bizarre quantum mechanics is. The story is told as though Schrödinger invented an example to teach people that objects really do exist in contradictory states until someone looks. Schrödinger was much less comfortable with that conclusion. He was showing how bizarre the situation became if the quantum state was treated as a straightforward picture of physical reality, and then extended without restriction. There is an important difference between saying that quantum theory represents a system using a superposition and saying that an ordinary cat literally possesses two classical biological conditions in the everyday tense. Schrödinger was challenging people to explain that difference. Where does the quantum description stop? If it stops at the radioactive atom, why? If the atom interacts with a detector, surely the detector becomes physically affected by the atom. You cannot pretend the detector is somehow outside nature. If the detector is included, why not the mechanism? If the mechanism is included, why not the cat? Eventually someone opens the box. Should that person be included too? This is where the thought experiment becomes much more serious than its popular version. The problem is not that a closed box hides information. The problem is that there is no obvious place to draw the line between the quantum system and the measuring apparatus. In ordinary laboratory practice, physicists often draw such a line because they need to perform calculations. One part of the experiment is treated quantum mechanically, another part is treated as a classical measuring device. This division works extremely well operationally. Schrödinger wanted to know whether it also made sense fundamentally. The measuring device is not made from special classical material, it is made from atoms. If atoms obey quantum mechanics, then in principle the device should obey quantum mechanics too. Once the device interacts with the system, their states become correlated. This produces what later became known as the measurement problem. Quantum theory allows a system to evolve into a combination of possible outcomes, while measurements seem to produce one definite result. Those two parts of the theory sit uneasily beside each other. There is the smooth quantum evolution that preserves superpositions, and then there is the measurement rule that tells us one outcome is observed. If both are fundamental, when does one process give way to the other? That is the uncomfortable question hiding behind the cat. Suppose the atom has not yet been measured. We use quantum mechanics to describe its possible decay, then the detector interacts with it. If we say the detector has performed the measurement, perhaps the quantum state collapses there, and the rest of the story becomes ordinary. But what exactly makes the detector capable of collapse? Is it size, complexity, irreversibility, the ability to create a permanent record? None of those answers was clearly built into the basic theory. Perhaps the collapse happens when the information reaches a human observer. Some early discussions of quantum mechanics encouraged this impression, although the history is more complicated than the popular version suggests. This leads to even stranger questions. Imagine a detector records the result but nobody checks it. Has the measurement happened? Place the result inside a computer and store it for a year. Does reality remain indefinite until someone opens the file? Imagine the cat itself sees the mechanism activate. Surely the cat qualifies as an observer of its own situation. The more seriously we take consciousness as the dividing line, the harder it becomes to define where physics ends and awareness begins. Schrödinger did not invent his cat to solve these questions. He invented it to make them unavoidable. There was another reason the example works so well. The difference between alive and dead is not subtle. Quantum experiments often involve outcomes that feel remote from ordinary experience. A detector clicks here rather than there. A particle has one measured property rather than another. It is easy to accept unfamiliar language when the objects themselves are unfamiliar. Schrödinger attached the quantum event to something macroscopic, complicated, and biologically obvious. Nobody needs a physics degree to understand the difference between a living cat and a dead one. By amplifying a tiny quantum possibility into such a dramatic difference, he showed that the problem could not simply be dismissed as something strange that only happened to atoms. Either quantum mechanics somehow stops applying before we reach the cat, or we need a better explanation of how definite macroscopic reality emerges from quantum descriptions. That challenge still matters. Modern physics has developed a much deeper understanding of how quantum systems interact with their environments. Decoherence, in particular, helps explain why large objects do not display obvious superpositions in daily life. The environment becomes rapidly entangled with different possible states, making interference between those states effectively impossible to observe. Schrödinger did not have the modern theory of decoherence available when he introduced the cat. If he had, some parts of the discussion would have looked different. Even so, decoherence does not make his original concern meaningless. It gives a powerful account of why the different possibilities begin to behave like separate classical alternatives. But philosophers and physicists still debate whether it fully explains why one particular result is experienced. That is where interpretations begin to separate. Some physicists say that asking what happens beyond the predictions is unnecessary. Quantum mechanics tells us the probabilities of observations, and that is what a physical theory should do. Others want a more direct account of reality. Some accept a genuine collapse process. Some argue that every outcome remains in a larger branching quantum state. Some introduce additional variables. Some change the dynamic so that large superpositions spontaneously disappear. Schrödinger's cat continues to appear in all of these discussions because the basic challenge remains easy to state. How do we get from a quantum description containing alternatives to the definite world in front of us? The disagreement between Schrödinger and some of his contemporaries was therefore not a disagreement between someone who believed quantum mechanics and someone who did not. It was a disagreement about how seriously to take different parts of the theory as descriptions of reality. Schrödinger knew that quantum mathematics worked. What worried him was the idea of identifying the mathematical state too directly with a literal physical situation. If the mathematical description contains a combination of alternatives, does that mean the physical world itself contains those alternatives in exactly the same way? The cat was his warning against answering too quickly. There is a useful comparison here with a weather forecast. Suppose a forecast gives a chance of rain tomorrow. Nobody concludes that tomorrow is physically existing in a mixture of raining and not raining, because the forecast contains both possibilities. The forecast describes our uncertainty about a future event. Quantum theory is not simply a weather forecast, because superpositions produce interference and other effects that ordinary probabilities do not. Still, Schrödinger worried about treating the mathematical object as though every feature of it could be translated directly into an ordinary picture of reality. He had already seen how easily that could become strange. The cat exaggerates the problem until the translation breaks. There is also some irony in the fact that Schrödinger himself helped create the mathematical framework that made the thought experiment possible. His famous equation describes the evolution of quantum states over time. Under that evolution, a superposition does not suddenly disappear merely because the system becomes inconveniently large. If systems interact, they can become entangled, and the combined state grows more complicated. The measurement rule then seems to introduce something different. Instead of continuing as a superposition, one definite outcome is recorded. Why should measurement be governed by a special rule? That question bothered many physicists. It still does. For Schrödinger, the cat was a way to point at the seam between those two descriptions. Before measurement, quantum evolution. After measurement, definite outcome. What happens at the seam? Calling it measurement does not explain the physical process any more than calling a mysterious noise from downstairs a noise explains why your cat has knocked over another plant. A label can identify the problem without solving it. This is one reason the original thought experiment is more interesting than the version usually repeated in popular culture. The familiar line that the cat is both alive and dead until someone looks makes the situation sound as though Schrödinger had confidently stated a rule. His actual intention was much closer to asking whether such a rule could really be taken literally. He wanted his readers to feel the absurdity. If a theory allowed this consequence, perhaps something about the interpretation needed more thought. There was also a broader philosophical disagreement running beneath all of this. Einstein and Schrödinger hoped science could describe an objective physical reality existing independently of observation. They were uncomfortable with interpretations that seemed to make measurements unusually fundamental. Bohr believed the demand for that kind of classical picture might itself be misguided. Quantum theory, in his view, had taught physicists that the conditions of measurement were inseparable from what could meaningfully be said about the result. The disagreement was not resolved by one decisive conversation. It became one of the great continuing debates in the foundations of physics. For many working physicists, this debate did not prevent progress. You can design a transistor, calculate atomic spectra, or operate a laser without first settling whether the quantum state represents physical reality, information, possibilities, or branches of the universe. That practical success sometimes encouraged an attitude of simply using the theory and avoiding the philosophical questions. Schrödinger's cat has survived partly because it makes avoidance difficult. The moment you tell the story properly, someone eventually asks whether the cat really is alive and dead. Then you have to explain what you mean by really. From there, you're already inside the measurement problem. It is also worth remembering that Schrödinger chose a living creature because life makes the consequences emotionally obvious, not because biological systems possess some special quantum status. The cat could have been replaced with a device that breaks a glass, fires a flag, or destroys a painting. Those examples would preserve the logical structure. A living animal simply makes the contradiction feel sharper. There is no gentle middle ground between alive and dead in the way the thought experiment is constructed. That sharp contrast forces the theory to confront a definite macroscopic difference. The experiment therefore functions like a magnifying glass for interpretation. Take one small ambiguity in how we speak about quantum states, amplify it through a detector and mechanism, and the ambiguity becomes enormous. Schrödinger had found a remarkably efficient way to turn an abstract problem into a story anyone could repeat. He may not have expected the cat to become more famous than much of his actual scientific work, but memorable animals have certain advantages over mathematical discussions. The important part is remembering why the animal entered the story. It was not there to tell us quantum mechanics is weird. Physicists already knew that. It was there to ask whether one popular way of understanding that weirdness was actually coherent. If the quantum state describes physical reality completely, and if ordinary physical interactions spread quantum correlations from small systems to large ones, then the cat seems to become trapped inside the same description. If that conclusion is unacceptable, something else has to happen. Perhaps the quantum state collapses. Perhaps the measurement device plays a special role. Perhaps the environment changes the situation. Perhaps all outcomes continue. Perhaps the state is not the kind of object we thought it was. Every interpretation must provide some account of the box. That is the lasting success of Schrödinger's challenge. He didn't need a real laboratory. He did not need a real animal. He needed only a setup simple enough that no one could avoid choosing what they believed the theory was saying. And once we see the cat in that historical role, the next question becomes much sharper. Saying that Schrödinger wanted to expose a problem is one thing. Explaining what the problem actually does during a measurement is another. Somewhere between the quantum possibilities before the detector responds and the single result recorded afterward, our description seems to change, and that change is where the measurement problem becomes impossible to avoid. Once superposition is taken seriously, the next problem appears almost immediately. Quantum mechanics can describe a system using several possible outcomes together, and those possibilities can interfere while the system remains sufficiently isolated. Then an experiment is performed, and something very different seems to happen. A detector gives one result, a pointer settles in one position, a screen records one event. The scientist writes one answer in the notebook. We do not usually experience a measurement as a hazy collection of several outcomes waiting politely for us to choose our favourite. Something definite appears. The difficult question is how a description containing possibilities becomes the single reality we actually observe. This is the quantum measurement problem, and Schrödinger's cat was designed to make it impossible to ignore. It helps to begin with an ordinary measurement because ordinary measurements seem so straightforward that we rarely think about what they involve. Suppose you want to know the temperature of a cup of water. You place a thermometer into it and wait. The thermometer interacts with the water, eventually reaches a reading, and you look at the result. Nobody imagines that the water had no temperature until the thermometer arrived. We assume the thermometer discovered something that was already physically there. The measurement may disturb the water slightly, but the basic picture is clear. There is an object with a property, there is a measuring device, and the device reveals the value of that property. Classical physics encourages this way of thinking because it works extremely well for the things we encounter in everyday life. Quantum measurement is less comfortable. A quantum system may be prepared in a superposition of different possible measurement outcomes. Before the measurement, the theory does not always describe the system as secretly possessing one of those outcomes in the ordinary classical sense. Then the measuring device interacts with it, and one result is recorded. If the measurement is repeated using identically prepared systems, different outcomes may appear on different trials, but the overall frequencies follow the probabilities predicted by quantum mechanics. The theory is extraordinarily good at telling us how often each result should occur. What becomes difficult is explaining what physically happened when one particular result appeared. The problem is easy to hide when the measuring device is treated as something separate from the quantum system. We might say that the electron is quantum, the detector is classical, and when the electron reaches the detector, a measurement occurs. That gives us a practical rule. Before measurement, use the quantum description. After measurement, record the result. For laboratory work, this can be perfectly effective. The difficulty begins when we remember that the detector is also a physical object. It is built from atoms. Those atoms are made from the same quantum ingredients as everything else. If quantum mechanics is supposed to describe matter, there seems to be no obvious reason why the detector should be exempt. Imagine a very simple measurement device with two possible readings. If the quantum system produces one outcome, the pointer moves to the left. If it produces another outcome, the pointer moves to the right. Before the interaction, the quantum system is in a superposition associated with both possible results, while the pointer waits in its starting position. The system then interacts with the device. If we allow ordinary quantum evolution to describe the entire process, the result is not simply one pointer position being chosen. Instead, the system and the pointer become correlated. One part of the combined quantum description contains the first outcome and the pointer on the left. Another part contains the second outcome and the pointer on the right. This is the same logic that led us from the radioactive atom to the cat. The quantum alternatives do not disappear just because they have reached a larger object. They spread into the measuring apparatus. If the pointer then activates another machine, that machine becomes correlated too. If a camera records the pointer, the camera becomes part of the physical chain. If a computer stores the result, the computer joins it. If a scientist reads the screen, the scientist's physical state becomes correlated with what was observed. At some point, however, the scientist experiences one result. That is the tension. The mathematical description seems capable of continuing as a combination of alternatives, while experience presents one definite outcome. Quantum theory therefore appears to contain two different kinds of change. One is the normal evolution of a quantum state, which can preserve and spread superpositions. The other is what is usually called collapse, where a measurement seems to reduce the possible outcomes to the one that was observed. The word collapse makes the process sound clearer than it really is. Something was spread across several possibilities, then it collapsed into one. Very tidy. Unfortunately, giving the change a name does not tell us what causes it. We still need to know when it happens, where it happens, and whether it is a genuine physical event or merely a change in the way we describe the system after learning the result? Suppose the radioactive atom inside Schrödinger's box has a possibility of decaying and a possibility of remaining unchanged during the chosen interval. If we say the quantum state collapses when the atom interacts with the detector, then the detector receives one definite result and everything afterward becomes ordinary. The cat is either alive or dead long before anyone opens the box. That sounds reasonable, but now we have to explain why the detector causes collapse. What property does it possess that the atom does not? Perhaps size is the answer. Maybe tiny systems can remain in superpositions while large systems cannot. But where exactly is the boundary? A detector can be made from smaller components. Molecules can display quantum behavior under suitable conditions. Larger systems can also show quantum effects when carefully isolated. Nature does not appear to carry a ruler that marks the point where quantum mechanics must stop. Perhaps complexity causes collapse. Once enough particles become involved, one outcome is selected. This sounds plausible, but again we would need a physical rule explaining how much complexity is enough and why. A complicated molecule may still behave quantum mechanically. A small engineered device can sometimes be placed into states that have no ordinary classical counterpart. Complexity certainly makes isolation more difficult, but difficulty is not the same thing as a fundamental law. Maybe irreversibility is the key. A measurement often creates a record that cannot realistically be undone. A detector clicks, a photographic plate changes, a computer stores information, heat spreads into the environment, the event becomes effectively permanent. This is much closer to how real measurements behave, but it creates another question. At the microscopic level, the underlying quantum interactions are still described by physical processes. If all those processes follow quantum rules, why should practical irreversibility suddenly select one unique result? The more carefully we ask what measurement means, the less obvious the answer becomes. This is one reason Schrödinger's cat is so useful. The detector inside the box is already a measuring device. It is designed specifically to determine whether radioactive decay occurred. If measurement alone creates a definite outcome, then the cat's fate should be decided as soon as the detector interacts with the atom. Opening the box later merely tells us what happened. In that case, the human observer is not doing anything physically special. But suppose someone insists that the quantum state remains unresolved until the box is opened and a person looks inside. Now consciousness seems to have entered the story. The cat would remain part of the superposition until information reached a mind capable of becoming aware of it. That possibility raises immediate difficulties. Why should a conscious observer have a special status in the laws of physics? Human beings are physical systems too. Our eyes absorb light. Signals travel through nerves. Neurons interact. Nothing obvious happens at the border of the skull that suddenly changes the rules governing matter. There is also the cat itself. If consciousness is what matters, the cat is presumably conscious enough to notice whether it is alive. It does not need a physicist to explain the situation. If the mechanism fails to activate, the cat continues experiencing the inside of the box. If the mechanism activates, the biological consequences occur. So does the cat count as the observer? If it does, the superposition should end before the scientist opens the box. If it does not, we need to explain why human awareness is special, while feline awareness is not. Which is probably not an argument anyone should attempt in front of a cat. The problem becomes even more interesting if we replace the cat with a machine. Imagine the detector records the result automatically. A camera photographs the reading. The image is stored on a computer. The computer sends a copy to another computer in a locked room. Nobody looks at any of it for a month. Did the measurement happen when the detector responded, when the photograph was taken, when the file was created, when the information was copied, or when a person finally opened the file? In practical physics, the answer is usually not mysterious. The detector and environment have already interacted strongly with the system. A stable record has been produced. We treat the measurement as complete. But the foundational question remains because the underlying quantum description does not contain a simple instruction saying that a sufficiently official-looking laboratory device has the authority to end a superposition. This is where decoherence begins to help. When a quantum system interacts with a measuring apparatus, the two become correlated. The apparatus then interacts with the environment. Air molecules collide with it. Light scatters from it. Heat moves through it. Information about the possible outcomes spreads into enormous numbers of surrounding degrees of freedom. The different alternatives become connected with different environmental states. Once this has happened, interference between the alternatives becomes effectively impossible to observe. The system no longer behaves like a delicate, isolated superposition that can easily recombine. From the point of view of ordinary experiments, the alternatives behave like separate classical possibilities. For a large measuring device, this process happens extremely quickly. For a cat, it is even more dramatic. A living animal is constantly interacting internally and externally. The idea of preserving a clean, coherent superposition of macroscopically different biological states in an ordinary box is completely unrealistic. The environment would carry away information about the alternatives almost instantly. Decoherence therefore explains a great deal about why the macroscopic world looks definite. It shows how ordinary classical behavior can emerge from quantum interactions without requiring someone to stare at the system. It removes much of the mystery surrounding the idea that human observation itself has magical powers. Yet decoherence does not automatically solve every part of the measurement problem. The reason is subtle, but important. Decoherence explains why interference between different outcomes disappears for practical purposes. It explains why the alternatives stop behaving like one coherent quantum combination that can easily produce interference. But if the complete quantum state still contains all the correlated alternatives, decoherence by itself does not select one of them as the unique actual result. Imagine that the quantum system begins with two possibilities. After interaction with the detector and environment, one part of the description contains the first result, a detector recording the first result, and an environment carrying information about the first result. Another part contains the second result, a detector recording the second result, and an environment carrying information about the second result. These alternatives no longer interfere in any accessible way. They look like separate classical outcomes. But why do you experience only one? That is where interpretations differ. If you believe a real collapse occurs, then at some stage one alternative is physically selected and the others disappear. Decoherence may help explain where and why that process becomes effective, but collapse must still be part of the story. If you believe there is no collapse, then both alternatives remain in the complete quantum description. Your experience of one outcome must be explained by the fact that different versions of the observer become correlated with different results. This is the route that eventually leads toward many worlds and related approaches. Other interpretations treat the quantum state in less literal ways. Perhaps the state represents an observer's information or expectations, rather than a physical object existing in the same sense as a table or an electron detector. In that case, collapse may simply represent an update when new information is obtained. Before measurement, several outcomes are possible from the observer's perspective. After seeing the result, the observer updates the description. This sounds familiar because we update probabilities all the time. Suppose you do not know whether it is raining outside. You assign possibilities to rain and no rain. Then you open the curtains. Your description changes immediately. Nobody thinks the weather physically collapsed because you look through the window. You simply learned what was already happening. The challenge is that quantum probabilities are not exactly like ordinary ignorance. Superposition and interference tell us that the alternatives have a structure beyond a simple list of unknown facts. So treating collapse purely as an update of knowledge raises the question of what underlying physical situation that knowledge refers to. The measurement problem survives because every apparently simple answer creates another question. Say the system has one definite result all along, and quantum mechanics only represents our ignorance. Then experiments involving quantum correlations and interference constrain what kind of hidden reality could lie underneath. Say the result is created by measurement, then define measurement physically. Say consciousness creates the result, then explain why consciousness should enter fundamental physics and what counts as conscious. Say decoherence creates classical reality, then explain whether decoherence actually selects one outcome or merely separates alternatives. Say all outcomes remain real, then explain what those multiple outcomes mean and why each observer experiences only one. There is no shortage of possible answers. The difficulty is finding one that preserves the successful predictions of quantum mechanics while also providing a clear account of reality. Another way to see the problem is to imagine performing the measurement very slowly. Instead of a detector that clicks instantly, suppose the measuring device changes gradually in response to the quantum system. At the beginning, the system is isolated. Then it begins interacting weakly with the apparatus. The apparatus starts carrying partial information. More interactions occur. The environment becomes involved. Eventually a stable record exists. At what exact instant did possibility become reality? If collapse is a physical event, perhaps there should be a precise point. But ordinary measurements do not necessarily provide one obvious dividing line. They are processes. Quantum information becomes correlated with increasingly large systems. Decoherence spreads, records become stable. By the time a human checks the apparatus, the outcome looks completely classical. The transition can therefore appear gradual in its physical development, even though the final experience is definite. This makes the phrase "when possibility becomes reality" slightly dangerous. It suggests there must be one dramatic moment when nature chooses. Some interpretations do say something like that happens. Others deny that any such moment exists. From one perspective, reality never contained several ordinary possibilities waiting for selection. The quantum state was simply the correct description, and measurement created a new relationship between system and observer. From another perspective, all the alternatives remain real, but become separated through decoherence. From another, collapse is genuinely built into nature, and becomes more likely as systems grow larger. The experimental predictions can be very similar, even when the stories behind them are radically different. That is what makes the measurement problem unusual. In many areas of physics, disagreement can be settled by measuring something more accurately. If one theory predicts one result and another theory predicts something else, build the experiment and see which survives. With interpretations of standard quantum mechanics, several different pictures can reproduce the same ordinary experimental predictions. The disagreement concerns what the formalism means, rather than what number appears on a familiar detector. There are attempts to turn some of these interpretations into experimentally distinct theories. Objective collapse models, for example, propose that superpositions really do break down through a physical process that becomes important for sufficiently large systems. If such models differ slightly from ordinary quantum predictions, increasingly sensitive experiments may be able to test them. That would move part of the measurement debate from interpretation into direct experimental physics. For now, however, much of the argument remains conceptual. Schrödinger's cat lives precisely in that conceptual gap. Before the box is opened, we know how to write the quantum description in principle. After the box is opened, the observer reports one result. The cat experiment asks what happened between those statements. Did the radioactive atom possess a definite condition before detection? Did the detector create the outcome? Did the environment effectively create classical alternatives? Did the state collapse? Did all outcomes continue? Did the observer merely update their information? Every answer changes what the cat story means. There is also a useful lesson here about the word reality. Physics does not normally require us to decide philosophical questions before doing experiments. Scientists can calculate probabilities, build detectors, compare predictions, and develop technology without agreeing on the ultimate nature of a quantum state. That is why quantum mechanics has progressed so successfully despite the measurement problem. The problem becomes unavoidable only when we ask what the mathematics is telling us about the world, when nobody is reading the instrument. This is exactly the question Schrödinger wanted to keep alive. A purely practical physicist might say that the detector gives a result, and that is enough. Use the theory, calculate the probabilities, move on. Schrödinger wanted more, Einstein wanted more. They wanted a physical picture that did not seem to divide the universe awkwardly into quantum systems on one side and mysterious measuring devices on the other. Niels Bohr was more willing to accept that the language of experimental outcomes had to play a fundamental role. For Bohr, our descriptions of quantum phenomena were inseparable from the experimental arrangements through which those phenomena became observable. He did not simply imagine an invisible classical world underneath the quantum mathematics waiting to be uncovered. This disagreement would shape what later became known broadly as the Copenhagen interpretation, although that label hides considerable differences between the physicists associated with it. The popular version often says that a quantum system remains in superposition until it is observed, at which point the state collapses. That description is useful as a rough introduction, but the historical and philosophical reality is more complicated. Still, it captures the question that matters for the cat. If collapse is part of the story, what exactly triggers it? If an observer is involved, what counts as an observer? And if the observer merely discovers a result that was already definite, why did we need the quantum superposition in the first place? Those questions take us directly into the argument over Copenhagen, collapse, and the strange role measurement seems to play in deciding what can be said about the quantum world. The phrase Copenhagen interpretation is often used as though it refers to one perfectly clear set of rules written down by a committee of physicists who all agreed on exactly what quantum mechanics meant. The historical reality is much messier. Niels Bohr, Werner Heisenberg, and other physicists associated with the development of quantum theory did not always express the same philosophical position, and their ideas changed over time. Even today, two people may say they accept the Copenhagen interpretation, while meaning somewhat different things. Still, the name has become useful shorthand for a broad family of ideas that places measurement at the centre of quantum mechanics, and warns us against assuming that microscopic objects possess all the familiar properties of ordinary objects before those properties are measured. This is where the question raised by Schrödinger's cat becomes especially sharp, because if measurement is what turns a quantum description into a definite result, then we need to understand what measurement actually is and whether the observer has any special role in making it happen. One of the instincts that quantum mechanics challenged was the idea that every physical object must carry a complete collection of definite properties at every moment. In classical physics, that assumption feels natural. A planet has a location even when nobody is looking through a telescope. A ball has a speed even if nobody measures it. A book on a table does not wait for you to enter the room before deciding which way its cover is facing. The properties belong to the object, and measurement reveals them. Bohr believed that this way of thinking could not simply be transferred unchanged to quantum systems. The outcome of a quantum experiment depended on the complete experimental arrangement, including what kind of measurement was chosen. Asking for a property without specifying how it would be measured could therefore be asking more from the theory than the physical situation allowed. This does not mean that Bohr believed ordinary objects disappear when nobody looks at them, or that human thoughts magically create atoms. Popular explanations sometimes compress the Copenhagen approach into the sentence reality does not exist until it is observed, but that is far more dramatic and much less precise than the ideas involved. Bohr was deeply concerned with what physicists could meaningfully say about experiments. Quantum systems were described using quantum theory, but the results of experiments had to be communicated in ordinary language and recorded by apparatus that produced definite outcomes. The measuring arrangement mattered because different experiments could reveal different aspects of a quantum system, and those aspects could not always be combined into one classical picture. A familiar example is the tension between wave-like and particle-like behavior. Arrange an experiment to reveal interference, and the quantum system displays behavior associated with waves. Arrange the experiment to determine a definite path, and the interference disappears. The point is not that the particle notices what the scientist wants and changes its personality to be helpful. The physical arrangement of the experiment is different. The interactions are different. The information that becomes available is different. Bohr called this kind of relationship complementarity. Different experimental arrangements can reveal different mutually exclusive aspects of the same quantum system, and trying to imagine all those aspects as simultaneously possessing ordinary classical reality can lead us into contradictions. This was a difficult idea for Einstein to accept. Einstein wanted a description of nature that went beyond the results of measurements. He hoped that physical reality existed with definite structure independently of what experiment anyone decided to perform. Bohr believed that quantum mechanics had taught physicists to be more cautious about making that demand. Their debates lasted for years and became famous partly because neither man was careless. Einstein repeatedly invented thought experiments intended to show that quantum mechanics was incomplete or inconsistent. Bohr repeatedly found ways to answer them. The discussions were not arguments between someone who understood quantum theory and someone who did not. They were disagreements between some of the people who understood it best. The question of collapse became one of the most memorable ways of expressing the disagreement. In the standard textbook picture, a quantum system can begin in a superposition of possible outcomes. While it remains unmeasured, the state changes according to the usual quantum rules. When a measurement occurs, one result is obtained, and the quantum state is updated to match that result. This change is often called collapse. Before measurement, several possibilities are represented. After measurement, only the observed possibility remains in the description. For students trying to calculate what a detector will show, this rule is extremely useful. It tells you what probabilities to assign before the measurement and what state to use after the result appears. The practical problem is usually solved. The philosophical problem has merely been moved into one word: collapse. What is collapsing? Is something physically changing in the world, or are we changing only our description because we have learned new information? If the collapse is physically real, what causes it? If it is not physically real, why does every observer experience a definite outcome? This is where a simple textbook rule begins turning into the measurement problem again. Imagine a single quantum system entering a measuring device. The device has two possible readings. According to ordinary quantum evolution, the system and the apparatus can become entangled. One possible outcome becomes correlated with one reading. The other becomes correlated with the other reading. Nothing in that smooth evolution automatically selects one branch and deletes the other. To obtain the experience familiar from a laboratory, we add the statement that measurement produces one definite result. That additional statement works, but it creates a boundary. On one side of the boundary, quantum systems can exist in superpositions. On the other side, measuring devices give definite answers. The difficult question is where the boundary belongs. This dividing line is sometimes called the Heisenberg cut. The name refers to the conceptual separation between the quantum system being studied and the classical apparatus used to measure it. In practice, the cut can often be moved. A detector may be treated as part of the classical measuring equipment in one calculation, while in another experiment some components of the detector might themselves be described quantum mechanically. The predictions remain consistent as long as the calculation is handled properly. That flexibility is useful, but it is strange if we expect the cut to represent a fundamental border in reality. If the line can be moved depending on how we choose to describe the experiment, perhaps it is not a physical wall at all. This was exactly the kind of problem that bothered Schrödinger. His cat takes the Heisenberg cut and forces us to ask where we intend to place it. Perhaps the radioactive atom is the quantum system, and the detector is classical. Then collapse occurs when the atom reaches the detector. But the detector is made of quantum matter, so perhaps we include the detector in the quantum system and place the cut at the mechanism. The mechanism is made of quantum matter too. Move the cut again, and the cat becomes part of the quantum description. Then the scientist opens the box. Now perhaps the scientist becomes the classical observer, but the scientist is also made of atoms. The line keeps retreating. If we are not careful, we end up with a universe divided into one enormous quantum system and some mysterious observer standing outside it, and there is nowhere obvious for that observer to stand. This is one reason the word observer has caused so much confusion. In everyday speech, an observer is usually a person. Someone watches something happen. In quantum physics, observation often refers much more broadly to a physical interaction that produces information about a system. A detector can observe in this practical sense. So can a photographic plate. So can an environment that becomes correlated with the system. Human consciousness is not required for a laboratory detector to register an event. Yet some interpretations of quantum measurement have given consciousness a more fundamental role, and these ideas became famous enough that they still influence popular discussions. One version says that the chain of quantum interactions can continue from system to apparatus to nervous system, but a definite result appears only when a conscious observer becomes aware of it. According to this view, consciousness completes the measurement. It certainly solves the problem of where to stop the chain. Unfortunately, it does so by creating another problem that may be even larger. What exactly counts as consciousness? Does a sleeping person count? Does a newborn baby count? Does a cat count? Does a mouse count? At what point in evolution did organisms acquire the ability to collapse quantum states? Was the early universe waiting billions of years for conscious life to appear before events could become definite? These questions do not automatically prove that consciousness-based interpretations are impossible, but they show how quickly the idea moves physics into difficult territory. There is also little need to invoke consciousness when describing ordinary quantum experiments. Detectors create stable records whether a person reads them immediately or not. A particle can trigger an electronic signal at midnight while the laboratory is empty. The data can sit on a hard drive until morning. When the scientists arrive, they do not normally think the experiment spent the night waiting in suspense for somebody to make coffee and check the results. The record already exists in the apparatus. If the apparatus has already produced a definite result, then the observer's mind seems unnecessary. But this returns us to the original question. Why did the apparatus produce a definite result? Calling it macroscopic is helpful but incomplete. Calling it a measurement simply repeats the problem. One response is that we should stop demanding a deeper picture. Quantum mechanics is not required to tell us what happens behind observations, in the same way classical physics once tried to do. It gives us the probabilities for possible experimental outcomes, and those predictions are what can be tested. Asking which outcome existed before measurement may be asking a question the theory does not define. This attitude is often associated with Copenhagen thinking, especially in its more practical forms. For many physicists, it is enough. The theory works. The apparatus gives results. Those results can be predicted. Science should focus on what experiments can establish, rather than inventing invisible stories that make us feel more comfortable. There is something refreshingly disciplined about that position. It also frustrates anyone who wants to know what the universe is actually doing. Imagine asking why a detector clicked and receiving the answer that quantum mechanics predicts a certain probability of a click. That may be scientifically correct, but it can feel as though the question has been answered sideways. You wanted to know what happened. You were given excellent instructions for calculating how often it happens. Einstein found this deeply unsatisfying, and Schrödinger shared much of that discomfort. The disagreement was partly about what we should demand from a physical theory. Must a theory provide a picture of an observer-independent reality? Or is it enough for the theory to organise and predict the outcomes of possible experiments? Quantum mechanics made this old philosophical question impossible to keep outside physics, because the mathematical formalism seemed to treat measurement differently from ordinary evolution. The cat then made the difference impossible to hide. There is another subtlety that gets lost when Copenhagen is reduced to the slogan, "Observation causes collapse." Bohr himself did not describe measurement as a mysterious mental event. He emphasized that experimental results must be described in classical terms, because an experiment requires a definite arrangement and a definite record. The apparatus establishes the conditions under which a physical quantity can be meaningfully discussed. This is different from saying a conscious person creates the outcome by looking. The distinction matters. When a detector measures whether the radioactive atom decayed, the detector is not merely revealing a hidden classical fact in the simplest sense. The quantum event and the measurement arrangement form one physical situation. The outcome belongs to that arrangement. From this perspective, asking what the atom was doing independently of every possible measurement may not always have a meaningful answer. Schrödinger's cat was partly aimed at showing how difficult it becomes to maintain this distinction once measuring devices are themselves included inside the quantum description. If the apparatus must be classical for measurements to make sense, why is it classical? What gives it that status? Bohr might answer that the distinction is functional rather than fundamental. In any actual experiment, some part of the world must serve as the measuring context in which results are defined and communicated. We do not need to describe the entire universe quantum mechanically at once. That works extraordinarily well in practice. Schrödinger wanted to know whether it told the whole physical story. The disagreement can seem strangely familiar if you imagine two people arguing about a map. One person says the map is excellent because it gets you everywhere you need to go. The roads are accurate. The distances work. You never get lost. The other person agrees but keeps asking what the landscape itself is really like beyond what the map records. The first person says the map already contains everything relevant to navigation. The second keeps pointing out that a successful map is not automatically the same thing as the territory. Quantum mechanics is a much more sophisticated case, but the tension is similar. Is the quantum state a picture of physical reality? Is it a tool for predicting measurement outcomes? Is it information? Is it something else entirely? What you think collapse means depends heavily on how you answer that question. If the quantum state is a real physical object or condition, collapse looks like a real physical change. Something in nature abruptly changes when measurement occurs. If the quantum state represents knowledge, collapse can look more like learning. The system does not need to undergo a mysterious physical jump. The observer simply updates the description after receiving new information. Suppose you're told that a card has been placed face down on a table. Before looking, you assign possibilities to what the card might be. Turn it over and your uncertainty vanishes instantly. Nothing physical happened to the card at the moment your knowledge changed. Your description changed. A knowledge-based interpretation of quantum collapse uses an idea somewhat like this, although quantum states are much richer than ordinary probability distributions. The difficulty again is interference. Before measurement, quantum alternatives can influence one another in ways that ordinary unknown cards cannot. So if the quantum state is merely information, it must be a very unusual kind of information, governed by a structure that produces uniquely quantum effects. Another approach says collapse is not merely an update and not merely a convenient rule. It is a real process in nature. Perhaps superpositions genuinely break down once a system reaches a certain size or complexity. In such theories, the problem is solved by changing the dynamics. Small systems can remain in superpositions for long periods, while large systems collapse rapidly into definite states. This has an attractive feature. It removes the need for a vague boundary between quantum and classical worlds. The collapse process itself creates the boundary gradually. The larger the system, the harder it becomes for a superposition to survive. Such ideas are known broadly as objective collapse theories. Unlike purely interpretive differences, some objective collapse models can in principle make experimental predictions that differ slightly from ordinary quantum mechanics. Scientists can therefore search for tiny deviations that might reveal whether collapse is a genuine physical process. So far, standard quantum mechanics remains remarkably successful, but the possibility of testing alternatives is important because it turns philosophical disagreement into experimental science. Then there is the more radical response: perhaps collapse never happens. Perhaps the entire problem comes from adding collapse to the theory in the first place. If quantum evolution naturally takes a system in superposition and entangles it with a detector, then perhaps we should simply allow that evolution to continue. The detector becomes correlated with both possible outcomes. The observer becomes correlated with the detector. Each resulting branch contains an observer who sees one definite result. From inside a branch, nothing looks indefinite. One version of you sees the first outcome, another version sees the second. There is no single moment when nature chooses. All outcomes remain within the complete quantum state. This is the road toward the many worlds interpretation, and it replaces the mystery of collapse with the mystery of branching reality. Whether that feels like an improvement depends heavily on what sort of mystery you prefer. Schrödinger's cat works perfectly here because it makes the branching vivid. Instead of saying one microscopic result occurred and the other disappeared, the no-collapse picture contains a branch with a living cat and a branch with a dead cat. When the observer opens the box, the observer becomes correlated with those outcomes as well. One observer sees a living cat, another sees a dead one. Each experiences only one result and has no ordinary access to the other branch once decoherence has separated them. Schrödinger invented the cat to criticize a troubling conclusion, and later physicists developed interpretations that effectively accepted a version of that conclusion and built an entire picture of reality around it. Physics has a sense of humour, even if it takes several decades to deliver the punchline. Between collapse and many worlds sits another process that has become essential to modern discussions of measurement. We have already touched on it several times because it is impossible to talk about macroscopic quantum behaviour for long without encountering it. Decoherence does not require a conscious observer. It does not require a special measurement device. It begins whenever a quantum system becomes entangled with its environment. For a microscopic system carefully protected from outside interaction, coherence can survive long enough for different alternatives to interfere. For a large object, the surrounding environment constantly acquires information about its state. Photons scatter from it. Air molecules collide with it. Heat flows. Internal particles interact. The environment becomes correlated with different possible outcomes. As those correlations spread, interference between the alternatives becomes effectively inaccessible. The system begins to behave as though it were an ordinary classical mixture of distinct possibilities. This is extremely important for the cat. The cat inside Schrödinger's box is not actually waiting in some pristine isolated quantum state until a human lifts the lid. Long before that, the cat detector, air, walls of the box and surrounding environment have interacted an enormous number of times. Information about what happened has spread through the system. The different macroscopic alternatives have become decohered. From any practical point of view, they no longer interfere. This explains why the world we experience looks classical, even though its ingredients obey quantum mechanics. But decoherence brings us right back to the question Copenhagen leaves open. If the alternatives have stopped interfering, has one of them actually become real while the other disappears? Or have both simply become unable to communicate through interference? If collapse is real, decoherence may help explain why measurements look the way they do. But something still has to select the outcome. If collapse is not real, decoherence explains why different branches behave independently. But then we must decide what status those branches have. The observer no longer needs to be magical, but the interpretation problem remains. That is why modern discussions of Schrödinger's cat often spend less time asking whether a human gaze collapses the state, and more time asking what environmental interaction actually accomplishes. The box was never truly isolated, the cat was never a simple microscopic system, and measurement was never merely a person opening a lid. Long before the observer arrives, the surrounding world has already become deeply involved, and following that involvement carefully leads us directly into the process that makes quantum possibilities stop behaving like the delicate superpositions we can observe in controlled experiments. Once we stop treating observation as something that requires a human being to stare into a box, the problem begins to look different. The world is full of interactions whether anyone is watching or not. Light bounces from objects, air molecules collide with them, heat moves between them, surfaces vibrate, atoms interact with nearby atoms. Information about physical systems is constantly spreading into their surroundings. For a large object, this happens so quickly and through so many channels that keeping its quantum state isolated becomes almost impossible. This is where decoherence enters the story. Decoherence is one of the most important ideas for understanding why this strange behavior of quantum mechanics is so obvious in carefully controlled experiments and almost completely absent from ordinary experience. It does not require consciousness. It does not require a special observer standing outside nature. It does not require the universe to notice that someone has opened a lid. It begins with something much simpler. A quantum system interacts with its environment, and those interactions change what can happen to the superposition. To understand why this matters, return for a moment to a small quantum system that has been prepared in a superposition of two possibilities. Perhaps there are two possible paths through an experiment. If the system is kept sufficiently isolated, the two alternatives can remain coherent. Coherent means that the relationship between them is preserved well enough for interference to occur. When the alternatives are later brought together in the right way, they can reinforce or cancel one another, producing a pattern that reveals the presence of the superposition. The crucial point is that the alternatives have not become independent, ordinary possibilities. They remain part of one quantum state whose components can still influence the final result. Now, allow the system to interact with something else. Suppose a stray particle of light scatters from it. The direction of that light may depend on which alternative is present. Information about the quantum system has now become carried by the light. The system is no longer described completely on its own. Its state has become connected with the state of the scattered light. If another particle interacts, more information spreads, then another. Soon the surrounding environment contains many physical traces that are correlated with the different alternatives. This does not mean the environment understands anything. An air molecule is not taking notes. A photon is not deciding which path the particle used and sending a report to the laboratory. Information here means physical correlation. Different conditions of the system become connected with different conditions of the surroundings. If the system follows one alternative, the environment develops one pattern of interactions. If it follows another, the environment develops another. As those correlations accumulate, the clean relationship between the alternatives becomes inaccessible. Interference becomes harder and harder to observe. The superposition has not necessarily been destroyed by some sudden event. Instead, the quantum coherence that allowed its different components to interfere has spread into an enormous combined system involving the original object and its environment. This is decoherence. The process can happen astonishingly quickly. For a single, carefully protected particle, physicists may preserve coherence long enough to perform an experiment. They remove air from the chamber, they cool the equipment, they shield it from stray electromagnetic fields, they reduce vibrations, they control the interactions as precisely as possible. Every unwanted contact with the outside world is a possible route through which information can escape. That is why quantum experiments often require such extreme conditions. The experimenter is not trying to convince the particle to behave quantum mechanically. Quantum mechanics is already the underlying theory. The challenge is preventing the environment from becoming involved too soon. Large objects have the opposite problem. They are involved with the environment constantly. Consider an ordinary grain of dust floating in a room. It is tiny by human standards, but enormous compared with an atom. Light from the room scatters from it continuously. Air molecules strike it from every direction. It absorbs and emits thermal radiation. Internal vibrations move through it. Each of these interactions can become correlated with its position or other physical properties. If the grain of dust somehow began in a superposition involving two noticeably different positions, the surrounding environment would rapidly acquire information about which position was associated with which interactions. The two alternatives would lose observable coherence extremely quickly. The grain would begin to behave, for all practical purposes, like an ordinary object located somewhere definite. Move from the grain of dust to a cat and the situation becomes almost comical. A cat is warm, it breathes, its heart beats, its blood moves, its nervous system is active, molecules are constantly entering and leaving its body. Heat is radiated into the surroundings, air interacts with its fur, sound waves move through the box. Chemical reactions occur in vast numbers every moment. The cat contains an enormous collection of subsystems, each interacting with the others and with the environment. Trying to preserve a coherent superposition involving two dramatically different biological conditions of the entire animal would be so difficult that an ordinary sealed box does essentially nothing to help. This is one of the biggest differences between the popular version of Schrödinger's cat and the actual physical situation. People often imagine that closing the lid isolates the cat from the universe. It does not. The lid mainly isolates the cat from the person standing outside. Inside the box, interactions continue everywhere. The detector interacts with the radioactive material. The mechanism interacts with the detector. The cat interacts with the air, the box, the mechanism, and itself. Heat spreads through the system. Molecules collide. Information about the physical outcome becomes distributed across enormous numbers of particles. Long before anyone opens the box, the alternatives associated with the different macroscopic outcomes have become thoroughly decohered. This helps explain something that would otherwise be very puzzling. If the world is made from quantum systems, why do we not routinely see ordinary objects in obvious superpositions? Why is your chair not visibly in two places at once? Why does your cup not interfere with another possible position of itself? Why does your cat not appear partly on the sofa and partly under the bed in the quantum mechanical sense? The answer is not that quantum mechanics stops applying when objects become large. The answer is that large objects interact with their environment so strongly that observable coherence between macroscopically different alternatives disappears extraordinarily quickly. The quantum rules remain underneath. The interference becomes unavailable. This distinction matters because it avoids the need to invent a sharp boundary where quantum physics suddenly becomes classical physics. There does not need to be a particular number of atoms beyond which quantum mechanics switches off. Instead, classical behavior can emerge gradually through interaction with the environment. A small system that is well isolated can display obvious quantum interference. A larger system may also display quantum effects if it is carefully controlled. As size, temperature, complexity, and environmental coupling increase, maintaining coherence becomes progressively harder. The classical world can therefore emerge from quantum mechanics without requiring nature to keep two separate sets of fundamental rules, one for tiny objects and another for everything large enough to appear in a kitchen. This was a major advance in understanding the measurement problem because it showed why measuring devices behave so differently from isolated microscopic systems. A detector is large and strongly connected to its surroundings. When a quantum event affects the detector, the result is rapidly amplified. An electrical signal may be produced, a current may flow, a screen may change, a physical record may form, then the environment interacts with that record. Information spreads outward. the alternatives associated with different detector readings become effectively unable to interfere. The device begins to behave like something with a stable classical outcome. From the perspective of practical laboratory work, this is exactly what we need. We send in a quantum system. The detector responds. A result becomes recorded. Nobody needs to wait for a conscious observer to arrive. The apparatus has already become entangled with the environment, and the relevant alternatives have decohered. Suppose the experiment runs overnight in an empty laboratory. A detector registers an event at 3 in the morning. The computer stores the reading. Nobody sees it until breakfast. Decoherence gives us no reason to believe that the result remained in some delicate laboratory superposition, while everyone was asleep. The apparatus and environment have already interacted so extensively that interference between macroscopically different records is effectively gone. The computer does not need a graduate student to stare at it before becoming part of the ordinary reality. This removes a great deal of unnecessary mystery from the word observer. The observer does not need to be a mind. Physical systems observe one another in the loose experimental sense whenever they interact in ways that leave distinguishable records. A photon bouncing from an object can carry information about its position. An air molecule colliding with it can do the same. The environment is constantly gathering physical information. This is sometimes called environmental monitoring, though nothing conscious is involved. The world is continually becoming correlated with itself. That is one reason classical reality appears so stable. Once information about an outcome has spread into millions or billions of environmental degrees of freedom, reversing the process becomes practically impossible. In principle, quantum evolution does not necessarily erase information. The full state of the system and environment contains the correlations created by the interaction, but recovering the original coherent superposition would require controlling all those environmental details with extraordinary precision. Imagine trying to reverse every collision of every air molecule, every scattered photon, every tiny transfer of heat, and every internal interaction that occurred after the measurement. For even a modest macroscopic object, the task becomes fantastically unrealistic. For a living cat, it becomes beyond absurd. This practical irreversibility is an important reason measurements appear permanent. Once a record has spread into the environment, the world behaves as though the outcome has been fixed. A detector has clicked. A screen displays a result. A notebook contains a number. The result can be copied, photographed, remembered, and transmitted. Each copy creates more physical correlations. By the time several people have seen the result, the information has spread so widely that reconstructing the original coherent alternatives would require controlling a portion of the universe that has already become involved in the event. This is why measurement feels one-directional. Before the result, interference may be possible. After the result has been amplified and recorded, the alternatives behave like separate classical histories. There is a useful analogy here, though it should not be taken too literally. Imagine dropping a small amount of ink into a glass of water. At first, the ink occupies one region. Then it spreads. In principle, the motion of every molecule follows physical rules. If you knew the position and motion of every molecule and had perfect control over them, perhaps you could reverse the process and gather the ink back into its original shape. In practice, that is impossible. The information has become distributed through too many microscopic details. Decoherence has a similar flavor. Quantum phase information that was once accessible within a small isolated system becomes distributed into correlations with the environment. Nothing needs to vanish mysteriously. The information simply becomes hidden in a much larger combined state. The analogy is imperfect because quantum coherence is not literally ink, but it captures the important idea that information can spread without being fundamentally destroyed. This explains why decoherence is sometimes described as turning a quantum superposition into something that looks like an ordinary classical mixture. Suppose we begin with two coherent alternatives. Before environmental interaction, those alternatives can interfere. After strong decoherence, interference between them becomes effectively unobservable. If we look only at the original system and ignore the enormous environment, the situation behaves as though one ordinary possibility or the other exists with certain probabilities. This is extremely close to the classical world we experience, but close is not always the same as complete. Here we reach the subtle point that keeps the measurement problem alive. Decoherence explains why alternatives stop interfering in practice. It explains why measuring devices produce stable records. It explains why macroscopic superpositions are almost impossible to observe. It explains why the environment, rather than consciousness, is enough to make the world look classical. What decoherence does not automatically explain is why one particular outcome is the one you experience. Suppose the original quantum system has two alternatives. After interaction with the detector and environment, the complete quantum description can contain one large correlated alternative in which the first result occurred and another in which the second result occurred. The environment prevents those alternatives from interfering in any practical way. They behave independently. But if the complete state still contains both, which one is real? Decoherence by itself does not necessarily answer that. This is why people sometimes say that decoherence solves the practical measurement problem, but not every interpretational version of it. It tells us how classical-looking outcomes emerge. It does not, by itself, tell us whether only one outcome exists. If you already believe that collapse happens, decoherence fits naturally into the story. The environmental interactions explain why large-scale superpositions become unstable, and why measurements create robust classical records. Then a genuine collapse selects one outcome. If you believe there is no physical collapse, decoherence also fits naturally. The alternatives separate into effectively independent branches. Each branch contains a consistent macroscopic record. No branch needs to interfere with the others again. The same process can therefore support very different interpretations. That is one of the fascinating things about decoherence. It clarifies the physics while leaving part of the philosophical argument intact. Schrödinger's cat becomes a useful example again. Imagine the radioactive atom is initially described through decay and no decay alternatives. The atom interacts with the detector. The detector becomes correlated with those alternatives. The detector affects the mechanism affects the cat. Meanwhile, the environment interacts with all of them. Very quickly, the branch associated with decay becomes tied to an enormous environmental record of decay, triggered mechanism, and dead cat. The branch associated with no decay becomes tied to a different environmental record involving no trigger and a living cat. Those macroscopic alternatives no longer behave like two paths in a carefully controlled interference experiment. The environment has separated them too thoroughly. Opening the box does not suddenly create this separation. It happened long before. What opening the box does is connect the outside observer with one of the already decohered outcomes. The observer sees the cat in one condition. Their eyes, brain, memories, and surrounding environment become correlated with that result. From the observer's perspective, there is one definite experience. The question that remains is what happened to the other alternative? Did it disappear? Was it never physically real? Did collapse remove it? Does it continue in some other part of the quantum state? Decoherence is largely silent on that final question. This is why it would be misleading to say that decoherence proves the many worlds interpretation. It does not. It would also be misleading to say it proves collapse. It does not. Decoherence is a physical process that almost every serious interpretation of quantum mechanics must take into account. The disagreement concerns what we should say about the resulting alternatives. There is another important consequence of decoherence that helps explain why certain kinds of classical states dominate our experience. The environment does not treat every possible quantum superposition equally. Some states are more stable under environmental interaction than others. For example, the position of an ordinary object is constantly being monitored by scattered light and air molecules. States corresponding to reasonably definite positions tend to leave robust records in the environment. a delicate superposition of widely separated positions becomes decohered extremely quickly. This helps explain why the world appears to contain objects in definite locations. The environment effectively favours certain stable patterns that can survive repeated interactions. These stable states are sometimes discussed as the basis from which classical reality emerges. The idea is not that the environment intentionally chooses sensible states. Rather, some kinds of quantum information are copied into the environment much more effectively than others. Those are the properties we repeatedly encounter as stable facts. Think about a table in a room. You know where it is because light scatters from it into your eyes. Someone else can look and agree. A camera can record it. Air interacts with it. The floor supports it. Countless environmental interactions carry redundant information about the table's location. You do not need direct access to every atom in the table. The environment has already made its macroscopic properties available through many separate channels. This redundancy helps create the shared objective world of everyday experience. Several observers can independently obtain the same information because the environment contains many copies of it. That begins to explain something even more fundamental than why one person sees a definite result. It helps explain why different people agree about what happened. If you open Schrödinger's box and find a living cat, another observer standing beside you will also see a living cat. The camera will record a living cat. The air, light, and surrounding objects will become correlated with the living cat. A consistent macroscopic record spreads outward. You do not encounter one result while your friend encounters a contradictory one in the same branch of ordinary experience. The environment stabilizes and distributes the record. This is part of the reason classical facts feel public rather than private. Quantum mechanics begins with states that can contain alternatives. Decoherence helps explain how stable records emerge that many observers can agree on. That does not mean the foundations are completely settled. It means one of the biggest pieces of the transition from quantum behavior to ordinary experience can be understood through physical interactions rather than through mysterious acts of awareness. It also explains why the quantum world seems hidden, even though everything around us is made from quantum matter. We do not need to travel somewhere special to find quantum mechanics. It is present in every atom of the room. The reason we do not see obvious interference between different versions of the room is that the room is hopelessly entangled with its environment. Everything is interacting with everything else. Coherence between large-scale alternatives disappears so rapidly that the classical description becomes overwhelmingly effective. The world looks ordinary because the environment is extraordinarily good at destroying the conditions required for obvious quantum strangeness. This gives Schrödinger's cat a somewhat different meaning from the one it had in 1935. Schrödinger imagined the cat partly to show how absurd it seemed to extend quantum superposition into the macroscopic world. Modern decoherence theory shows why we should not expect a real macroscopic cat to display observable interference between life and death states. The cat is too entangled with its surroundings. Its quantum alternatives would decohere almost instantly. That resolves one part of the puzzle that Schrödinger could not fully analyze with the tools available at the time. But the cat still refuses to leave quietly because the deeper question remains. After decoherence, if the full quantum description still contains several non-interfering alternatives, what should we say about them? One answer is that only one survives because collapse is real. Another is that the quantum state is not a literal catalogue of equally real worlds in the first place. A third is that every decohered alternative continues, with each becoming part of a different branch of reality. Once decoherence has explained why those branches no longer interfere in any noticeable way, the idea of multiple outcomes existing without contradicting our single experience becomes much easier to formulate. That is where the cat begins leading us away from the question of why the quantum world looks ordinary, and toward a stranger question about what becomes of all the possibilities we no longer see. Once decoherence has separated the different outcomes so thoroughly that they no longer interfere in any noticeable way, we're left with a question that is both simple to ask and surprisingly difficult to answer. What happened to the alternatives we no longer experience? If the quantum description began with several possibilities, and the environment caused those possibilities to behave like separate classical outcomes, does only one of them remain real, or do the others continue in some form? Quantum mechanics gives us excellent predictions for what we will observe, but it does not force every physicist to tell the same story about what exists behind those observations. This is where interpretations begin to multiply. Some remove the unused possibilities through collapse. Some say the possibilities were never physical objects in the first place. Some propose deeper hidden properties beneath the quantum description, and one of the most famous approaches simply refuses to delete anything at all. That last approach is usually called the many worlds interpretation. The basic idea sounds extravagant when first heard, but it begins with a surprisingly conservative move. Instead of adding a special collapse process to quantum mechanics, many worlds says that the ordinary quantum evolution should simply continue. If the theory says a system develops into a superposition of different outcomes, then the complete state continues to contain those outcomes. Nothing suddenly chooses one and removes the others. Measurement is not a special exception to the normal rules. It is simply another physical interaction. Imagine the radioactive atom inside Schrödinger's box again. One alternative involves decay, another involves no decay. The atom interacts with the detector. The detector becomes correlated with those alternatives. The mechanism becomes correlated with the detector. The cat becomes correlated with the mechanism. The environment becomes correlated with the entire arrangement. Decoherence rapidly prevents the resulting alternatives from interfering with one another. In a collapse interpretation, one of those alternatives eventually becomes the actual result, and the other disappears from the physical description. In many worlds, neither disappears. One branch contains a living cat, another contains a dead cat. When the observer opens the box, the observer also becomes part of the branching structure. In one branch, the observer sees the living cat. In another, the observer sees the dead cat. Each version of the observer experiences one definite outcome. Neither feels divided. Neither sees a blurry mixture. Each believes a single result occurred because within that branch, a single result did occur. This is the part that makes many worlds sound like science fiction. It appears to multiply reality every time a quantum event has several possible outcomes. The phrase many worlds encourages the image of entire universes splitting like roads at a junction, producing countless copies of everything. One version of you drinks tea. Another chooses coffee, one catches the train, another misses it. Somewhere, perhaps, there is a version of you who remembered every password they have ever created, although that may be asking too much even from an infinite quantum universe. The actual interpretation is more careful than the popular picture suggests. It does not necessarily say that every ordinary human decision creates a magical new universe, because you hesitated between two breakfast options. The branching comes from quantum interactions and decoherence. Large-scale events may become associated with different decohered outcomes because the microscopic processes underneath them evolve differently. The branches are not separate places floating next to one another in space. They are effectively independent components of the larger quantum state. The appeal of many worlds is that it removes the need for collapse. The same quantum rules apply everywhere. There is no special boundary between microscopic systems and measuring devices. There is no moment when nature suddenly changes its behavior because an apparatus has become large enough. There is no need for consciousness to finish the measurement. The detector, cat, observer, and environment all obey the same physics. This solves one of the problems Schrödinger was pointing toward. If quantum mechanics applies universally, then let it apply universally. Do not stop the description when it becomes uncomfortable. Of course, that solution comes with a price. You must accept that the alternatives in the quantum state are not merely discarded possibilities. They continue as parts of reality. For some physicists, this is cleaner than collapse. For others, it is an enormous amount of reality to accept simply to avoid one special rule. There is also the problem of probability. If all outcomes occur, what exactly does it mean to say one outcome has a certain probability? Before opening the box, the observer knows that every allowed branch will exist in the many worlds picture. So why should one result be considered more likely than another? Supporters of many worlds have developed arguments showing how the usual quantum probabilities can emerge from the structure of branching and from rational expectations of observers who do not yet know which future branch they will experience. The details are still discussed and debated. This is an example of how removing one mystery can expose another. Collapse asks why one outcome is selected. Many worlds avoid selection, but must explain why probability still feels meaningful when all outcomes occur. Schrödinger himself was not proposing many worlds when he invented the cat. The interpretation was developed later, most famously through the work of Hugh Everett in the 1950s. Everett disliked the special role given to measurement in standard accounts of quantum mechanics. He wanted a description that treated observers as physical systems inside the universe, rather than as special entities standing outside it. That idea has a certain elegance. After all, there is no laboratory outside the universe where someone can observe everything from a safe classical distance. If quantum mechanics is a universal theory, then observers themselves must somehow fit into the quantum description. Everett's approach did exactly that. The observer measures the system and becomes correlated with the result. No collapse is required. The full state contains the different observer outcome combinations. At first, the idea received relatively little attention. Over time, especially as decoherence became better understood, many worlds gained more serious interest. Decoherence provided a physical explanation for why different branches would stop interfering and therefore behave like independent classical histories. Without decoherence, the idea of branching worlds is much harder to make precise. With decoherence, the branches become natural structures within the quantum state. Many worlds is only one attempt to deal with the cat. Another possibility is that quantum mechanics does not give us the complete physical description. Perhaps there are hidden properties underneath the quantum state that determine what actually happens. In that case, the apparent uncertainty of quantum mechanics might arise because we do not know those deeper variables. This idea is attractive because it resembles ordinary uncertainty. A coin toss looks random because we do not track every detail of the coin, the air, the hand, and the table. If we knew the complete physical state perfectly, classical mechanics would in principle determine the result. Perhaps quantum randomness works similarly. Maybe particles have definite properties and trajectories, but quantum mechanics only gives us incomplete information about them. Einstein hoped for something along these lines, although he did not provide a finished hidden variable theory that replaced quantum mechanics. He believed that the probabilistic description might be evidence that the theory was incomplete. The difficulty is that experiments have ruled out many simple versions of hidden variables, particularly models in which particles carry purely local instructions, independent of distant measurement choices. This does not mean every hidden variable theory is impossible. One famous example survives. It is usually called Bohmian mechanics, named after physicist David Bohm, although related ideas had been proposed earlier by Louis de Broglie. In Bohmian mechanics, particles have definite positions at all times. They do not exist as vague clouds of location waiting for measurement. The quantum state still plays an essential role, but it guides how those definite particle positions evolve. From this perspective, the cat inside the box is never literally both alive and dead. The particles making up the cat have one actual configuration. The quantum description may contain different possible branches, but only one branch contains the actual configuration of particles. If the radioactive event follows the decay path, the mechanism activates and the cat dies. If it follows the other path, the cat lives. The uncertainty belongs to our lack of knowledge about the exact configuration. That sounds much closer to classical intuition, but Bohmian mechanics has its own unusual feature. It is explicitly non-local. distant parts of an entangled system can be connected in a way that cannot be explained through ordinary local influences moving between them in the simple classical picture. Experiments involving entanglement tell us that any hidden description, preserving the predictions of quantum mechanics, cannot remain comfortably local in the way Einstein originally hoped. So Bohmian mechanics saves definite particle positions, but it does so by accepting a deeply non-classical connection between distant systems. Again, quantum mechanics offers no free escape. Choose the part of classical intuition you want to preserve, and something else usually becomes strange. Another family of approaches says that collapse is real. Instead of treating collapse as a vague measurement rule, these theories make it an actual physical process. A small isolated system can remain in a superposition. As systems become larger or involve more particles, the probability of spontaneous collapse increases. Eventually, one definite outcome appears. This approach is often called objective collapse because the collapse does not depend on a human observer. Nature does it automatically. A detector does not become classical because someone looks at it. A cat does not wait for consciousness. Large superpositions simply become unstable according to additional physical rules. This has an obvious attraction for Schrödinger's experiment. The radioactive atom can remain quantum. The combined system begins to grow. Once enough macroscopic matter becomes involved, the superposition collapses to one outcome. The cat is then either alive or dead. There is no need for many branches. There is no need for the observer to create the result. There is an actual physical mechanism that turns quantum alternatives into one classical reality. The challenge is that objective collapse theories modify standard quantum mechanics. Once you modify a successful theory, you must make predictions that survive experimental testing. This is actually a strength as well as a risk. If an objective collapse model predicts tiny deviations from standard quantum behavior, scientists can search for them. Experiments with increasingly large superpositions can test whether quantum mechanics continues to work without collapse at scales where alternative theories expect something different. So far, quantum mechanics has survived an impressive range of such tests, but experiments continue to push into new territory. A different approach avoids making strong claims about hidden mechanisms or branching worlds, and focuses instead on what the quantum state means for an observer. Some interpretations treat the quantum state primarily as a representation of information, expectations, or relationships, rather than as a literal physical object spread across reality. From this perspective, asking which parts of the quantum state are physically real may already be the wrong question. Consider the state of the cat before you open the box. You know the setup. You know the possible outcomes. You can assign probabilities. When you look inside, you gain new information and update your description. The change in the quantum state may therefore resemble a change in what you know, rather than a physical collapse occurring somewhere in space. This does not reduce quantum mechanics to ordinary ignorance. The probability rules and superposition structure remain genuinely quantum, but it changes what we think the mathematical state represents. One example of this general direction is an interpretation in which quantum probabilities are understood as an observer's personal expectations about future experiences. Another emphasizes that physical properties are meaningful only relative to other systems with which they interact. These approaches can sound less dramatic than many worlds, but they raise their own questions. If the quantum state is information about what? If properties are relative, what gives us the stable shared world that different observers seem to agree on? Decoherence can help with part of that answer, because the environment creates many consistent records that different observers can access. Still, the interpretation has to explain how those records fit into its picture of reality. There is also an approach sometimes described through consistent histories. Instead of asking for one quantum state that tells a simple story at every moment, this framework considers sets of possible histories that obey rules, allowing probabilities to be assigned consistently. Certain histories can be treated as alternatives without requiring them to interfere with one another. From this perspective, The cat can be discussed through a consistent set of histories in which one history contains decay and death, while another contains no decay and survival. The emphasis shifts away from a dramatic moment of collapse and toward which collections of histories can be meaningfully treated as alternatives. This is another example of the same pattern. The experimental predictions remain familiar. The story about what those predictions mean changes. There are even interpretations that try to avoid giving the quantum state a universal meaning at all. They focus on relationships between systems, arguing that a property may be definite relative to one system while described differently relative to another. Imagine the detector inside the box has interacted with the radioactive atom. Relative to the detector, a definite correlation may already exist. The observer outside has not yet interacted with the box and therefore uses a different quantum description. When the observer opens the box, the descriptions become correlated. This approach tries to remove the need for one absolute viewpoint from which the entire universe must have a single state known from nowhere. It is a very different way of thinking from classical physics, but relativity had already taught physicists that some quantities depend on the relationship between observers. Quantum theory may require an even deeper form of relational thinking. With all these possibilities available, it is natural to ask which interpretation physicists believe. There is no single answer. Some working physicists strongly favour many worlds. Some prefer collapse models. Some find Bohmian mechanics conceptually attractive. Some take a Copenhagen-style approach and avoid making claims beyond experimental outcomes. Some prefer information-based or relational interpretations. Many use quantum mechanics successfully, without committing strongly to any interpretation at all. A physicist can calculate the behaviour of an atom, design an experiment, and publish accurate results without first deciding whether the universe branches. That can seem surprising from outside physics. You might expect scientists to agree on what their most successful theory says reality is made of, but interpretations often agree on the measurable predictions available in ordinary experiments. If two interpretations tell you the detector will display exactly the same statistics, the detector cannot easily decide which interpretation is correct. This is why the debate has continued for so long. It is not merely because physicists enjoy arguing, although history suggests they are certainly capable of it. The theories can be empirically difficult to separate. There is another lesson hidden here. Schrödinger's cat is often presented as though quantum mechanics gives one outrageous answer. The cat is alive and dead until you look. The actual situation is almost the opposite. Quantum mechanics gives us a formalism that predicts experimental outcomes extremely well, while physicists disagree about the story that connects the formalism to reality. One interpretation says the cat occupies one actual outcome because collapse occurs. Another says the cat has one definite particle configuration, even though the quantum state contains other possibilities. Another says the complete state contains both outcomes in separate branches. Another says asking which outcome exists before the relevant interaction may be demanding an absolute fact the theory does not provide. The cat does not have one universally accepted philosophical status. It has become famous precisely because it sits where the interpretations separate. This also means there is no simple experiment where someone opens an actual box and proves one interpretation correct. Every ordinary version ends with one observed result. The cat is alive or dead. The observer records one outcome. The interpretations agree that this is what the observer experiences. They disagree about what else, if anything, exists beyond that experience. Many worlds says another branch contains the other outcome. Bohmian mechanics says only one particle configuration was actual. Collapse says the unused alternative was physically removed. Information-based approaches may say the question assumes too literal a meaning for the quantum state. All of them are trying to explain the same successful predictions. This can feel unsatisfying if you hoped physics had already chosen one clear answer. But it also reveals something important about science. A theory can be extraordinarily successful while leaving deep questions about interpretation open. Newtonian gravity predicted motion beautifully long before anyone understood gravity as curved space-time. Thermodynamics described heat before the microscopic theory of atoms became secure. Science often learns how nature behaves before it settles the best language for describing what that behavior means. Quantum mechanics may be another example, except that the gap has lasted much longer and reaches much deeper into our assumptions about reality. The cat keeps returning because it makes every interpretation show its cards. If you believe in collapse, explain what collapse is and why. If you believe in many worlds, explain what the branches are and how probability works. If you believe in hidden variables, explain the strange non-local connections required by experiment. If you treat the quantum state as information, explain what kind of reality supports that information. There is no option that simply restores the comfortable classical universe without paying a conceptual price somewhere. That may be the most important thing the cat teaches us. Quantum mechanics is not strange because physicists chose a strange interpretation. The experimental structure itself prevents us from keeping every piece of ordinary intuition. Something has to change. Perhaps definite properties are not always present before measurement. Perhaps locality must be weakened. Perhaps collapse is a new physical process. Perhaps all outcomes survive. Perhaps the quantum state is not a direct picture of reality. The interpretations differ mainly in which familiar ideas they are willing to give up, and once those alternatives are laid beside one another, the original question becomes much easier to state and much harder to avoid. Schrödinger's cat was never really asking whether one unfortunate animal could somehow be alive and dead in an ordinary box. It was asking what quantum mechanics is telling us about reality, when several possible outcomes appear in the theory, but only one appears in our experience, and answering that fully means returning to the cat one final time and separating the famous slogan from what the thought experiment actually says. So after all the boxes, detectors, radioactive atoms, arguments about measurement, disappearing interference, branching realities, hidden variables, and one imaginary cat that has somehow managed to survive nearly a century of physics discussions, we can finally return to the simplest question. What is Schrödinger's cat, really? The answer is much less mysterious than the popular slogan, and much more interesting than the idea of a cat literally waiting in a strange half-alive condition for someone to open a lid. Schrödinger's cat is a thought experiment about the problem of measurement in quantum mechanics. It was designed to show what happens when the strange rules used to describe microscopic systems are extended without explanation into the ordinary world of large objects. The cat is not the discovery. The cat is the warning sign. That distinction changes almost everything about the way the story should be understood. When people first hear about Schrödinger's cat, they are usually told that the animal is both alive and dead until somebody looks inside the box. It is a memorable sentence, which is probably why it has survived so well. Unfortunately, it can also make the thought experiment sound as though Schrödinger was proudly announcing one of the laws of quantum mechanics. Put a cat in a box, stop looking, and reality becomes confused. Open the box, and the universe finally decides what happened. That is not what he was trying to say. Schrödinger invented the example because he thought taking the quantum description too literally could lead to an absurd situation. He wanted people to notice the difficulty, not simply accept the cat as an ordinary consequence of nature. The real chain begins with something microscopic. A radioactive system is described using quantum mechanics. During a chosen period, there is a possibility of decay and a possibility of no decay. Those alternatives are connected to a detector. The detector is connected to a mechanism. The mechanism determines whether the cat survives. If we describe only the atom quantum mechanically and treat everything else as an ordinary measuring device, the story seems manageable. The atom is uncertain until the detector records an outcome, and then the rest follows. But the detector is itself made from quantum matter. So is the mechanism, so is the cat. If quantum mechanics applies universally, there is no obvious reason to stop the quantum description at the detector simply because the detector is large enough to have a label and a power cable. That is where Schrödinger presses the problem. If the microscopic alternatives become correlated with the detector, and the detector becomes correlated with the mechanism, then the alternatives seem to spread outward. One part of the description contains decay, an activated detector, a triggered mechanism, and a dead cat. Another contains no decay, an inactive detector, an untouched mechanism, and a living cat. If the mathematical description is treated as a direct picture of physical reality and nothing else happens, then the cat seems to become involved in the superposition too. Schrödinger's reaction was not to shrug and say that cats must simply be like that. His point was that the result should make us question how we were interpreting the theory. This also explains why simply saying the cat is unknown misses the issue. If you place an ordinary cat in a room and close the door, you may not know whether it is asleep on a chair or sitting beside the door waiting for you to return. There is nothing quantum about that uncertainty. The cat is already somewhere. Your lack of information does not create a physical combination of locations. The same is true for a coin hidden beneath a cup. You may not know whether it shows heads or tails, but you assume that one answer is already true. Quantum superposition is different because the alternatives in a quantum state can interfere while coherence is preserved. Their relationship can affect the results of experiments. That is why quantum uncertainty cannot always be reduced to ordinary ignorance. The possibilities are not merely labels for things we have failed to check. They form part of a physical description that produces measurable consequences. This is the first thing the cat is really about. It forces us to ask how a genuinely quantum superposition at a microscopic scale becomes connected to the definite outcomes of ordinary experience. The second thing the cat is about is measurement. Quantum mechanics gives us one kind of description before a measurement and a definite result afterward. In the traditional textbook language, the state collapses. Several possible outcomes are represented before measurement. One outcome is obtained after measurement. For calculating experiments, this rule works extremely well. The difficulty is that the word collapse does not tell us what physically causes the change. Does collapse happen when the radioactive atom interacts with a detector? If so, why is the detector special? Does it happen when a macroscopic record appears? If so, how large must the record become? Does it happen when information reaches a conscious observer? If so, why should consciousness have a unique role in fundamental physics? Does it happen naturally because large superpositions are unstable? That is the approach taken by some collapse theories. Or perhaps collapse does not happen at all, and the quantum state continues evolving while different outcomes become separated into effectively independent branches. Every answer changes what Schrödinger's cat means. This is why there is no single simple statement that every physicist would use to describe what is happening inside the box before it is opened. Physicists agree extremely well about the predictions of quantum mechanics. They disagree much more about what the mathematical state represents and what should be said about the alternatives after measurement. That can sound like a weakness, but it is useful to separate two different questions. One question is whether quantum mechanics predicts experiments correctly. On that point, the theory has been extraordinarily successful. The other question is what kind of reality best explains those predictions. That is where interpretation enters. The difference is important because people sometimes hear that physicists disagree about Schrödinger's cat and conclude that quantum mechanics itself must be uncertain or unreliable. It is almost the opposite. The theory works so well that the disagreement has survived precisely because several very different interpretations can reproduce the same experimental results. A detector does not care whether the physicist using it prefers Copenhagen, many worlds, Bohmian mechanics, or some other interpretation. The detector produces the same statistics. It is remarkably unhelpful in philosophical arguments. Modern physics has also changed the way we think about the box because we now understand decoherence much better than physicists did when Schrödinger first proposed the thought experiment. Decoherence explains why large objects do not normally behave like clean, isolated quantum superpositions. A small quantum system can sometimes be protected from its environment long enough for different alternatives to remain coherent and produce interference. A large object is constantly interacting with its surroundings. A cat takes this problem to an extreme. It is warm, it breathes, it emits heat. Molecules move through it. Light and air interact with it. Its internal parts interact with one another continuously. Information about its condition spreads into the environment at an enormous rate. Even inside a closed box, the cat is not isolated in the quantum mechanical sense. So a real cat inside an ordinary sealed box would not remain in a delicate coherent superposition, simply because a person outside could not see it. The environment inside the box would already be involved. The detector, mechanism, cat, air, heat, and walls would become correlated with the different outcomes. The alternatives would decohere extremely quickly. That is an important correction to the popular version. The human observer opening the lid is not normally understood as the first physical interaction that matters. Long before the lid moves, the system has already interacted internally in countless ways. This is why the idea that consciousness magically creates reality is not required by the experiment. A detector can record an event without anyone watching it. A computer can store the result. A camera can photograph the inside of the box. The data can exist for hours before a person checks it. Modern quantum physics does not need to wait for a human mind before ordinary environmental interactions become important. The more interesting question is what decoherence actually accomplishes. It explains why the different alternatives stop interfering in any observable way and why the world begins to look classical. It explains why large-scale records become stable. It explains why different observers can agree on what happened, because information about the outcome becomes copied into the environment. What it does not automatically do is choose one interpretation of the remaining quantum state. If you believe collapse is real, decoherence can help explain why macroscopic states become effectively definite before collapse selects an outcome. If you believe many worlds, decoherence explains why different branches stop interfering and behave like separate histories. If you favour another interpretation, decoherence still matters, but you may tell a different story about what those decohered alternatives represent. That is why the cat survives even after decoherence has explained so much. The old question has become more precise rather than disappearing. Now consider the many worlds answer. In that interpretation, the cat is not forced into one outcome by collapse. The complete quantum state contains a branch with the living cat and another with the dead cat. When the observer opens the box, the observer becomes correlated with those branches. One version experiences the living cat, another experiences the dead cat. Each sees one definite outcome because the branches no longer interfere in any practical way. This approach accepts something close to the conclusion Schrödinger originally wanted to make uncomfortable. Instead of saying the conclusion proves something has gone wrong, Many Worlds says perhaps the mistake was expecting the other alternatives to disappear. Then there is Bohmian mechanics, where particles have definite positions and one actual configuration. In that picture, the cat is never literally both alive and dead in the same sense. The underlying configuration follows one actual history, even though the quantum state contains a richer structure that guides the motion. This preserves definite outcomes, but accepts a form of non-local behaviour that is very unlike classical physics. Objective collapse approaches offer another answer. They suggest that sufficiently large superpositions physically break down. The atom may remain quantum, but as the chain grows to include more matter, a real collapse becomes overwhelmingly likely. The cat therefore ends up in one definite condition without requiring a conscious observer. Copenhagen-style approaches often avoid insisting on a detailed picture of what exists independently of measurement. The quantum state is used to predict possible outcomes, while the measurement arrangement provides the context in which a definite result becomes meaningful. From that perspective, asking for a classical description of the cat before measurement may demand something the theory was never designed to provide. Other interpretations focus on information or relationships between physical systems. They may say the state changes relative to an observer or interacting system rather than through one universal collapse that happens everywhere at once. There is no effortless option. Many Worlds preserves universal quantum evolution, but gives us branching reality. Bohmian mechanics gives definite configurations but accepts unusual non-local structure. Collapse theories restore one outcome by changing the standard dynamics. Copenhagen avoids some claims about hidden reality, but leaves people who want a deeper picture unsatisfied. Information-based and relational approaches change what we mean by the quantum state itself. Quantum mechanics seems determined to charge an admission fee for every comfortable explanation. This is probably the best way to understand why Schrödinger's cat remains useful. It is not an experiment that gives us one answer. It is a test for interpretations. Bring your favourite interpretation to the box and tell us what it says is happening. Does one outcome become real? Do both continue? Was only one actual all along? Is the quantum state describing reality-information relationships or something else? The cat forces every interpretation to reveal what it believes about measurement. There is also another misconception worth clearing away. Schrödinger's cat does not mean that anything uncertain is quantum mechanical. People jokingly describe unopened messages, untested exam results, missing deliveries, or food in the refrigerator as Schrödinger versions of those things. The jokes are harmless and occasionally quite good, but they are not the physics. If you have not checked whether there is milk in the refrigerator, the milk is not in a quantum superposition of existing and not existing simply because you are upstairs. There is already a macroscopic physical fact. You are merely unaware of it. The same applies to most everyday uncertainty. A result can be unknown without being in a coherent quantum superposition. What makes the original cat unusual is that its fate is deliberately tied to a microscopic quantum process. That connection is essential. The cat also does not prove that quantum effects only exist when nobody is looking. Quantum mechanics operates whether anyone is present or not. What matters is interaction. A quantum system that remains isolated can preserve coherence. A quantum system that becomes strongly correlated with its environment loses accessible coherence. A human gaze is simply one possible source of interaction among many. Nor does the cat prove that reality itself is fundamentally random in every interpretation. Standard quantum mechanics gives probabilistic outcomes, but some interpretations describe underlying processes differently. Bohmian mechanics, for example, is deterministic at the deeper level, even though observers still encounter quantum probabilities because they do not know the complete underlying configuration. The thought experiment, therefore, does not settle the question of determinism either. What it does settle is that we cannot understand the measurement problem simply by ignoring it. The transition from quantum possibilities to definite macroscopic experience needs some account. Schrödinger's achievement was to make that need visible. There is something almost funny about how effective the example became. Physicists had been discussing mathematical states, probability, measurement, and the foundations of quantum mechanics in highly technical language. Then someone added a cat, and suddenly the argument escaped into popular culture. It is easy to see why. A cat gives the problem weight. If the outcome is only a tiny detector reading, we can remain comfortably detached. If the outcome is whether a living creature survives, the difference between possibilities becomes impossible to treat as a technical detail. Schrödinger amplified the conceptual problem in exactly the same way the mechanism in the thought experiment amplifies the radioactive event. A microscopic uncertainty becomes a macroscopic consequence. A technical question becomes a memorable story. That is probably the most precise answer to what Schrödinger's cat really is. It is an amplifier for the measurement problem. The radioactive atom begins with quantum possibilities. The apparatus makes those possibilities visible at a larger scale. The cat pushes them into a form that clashes directly with ordinary experience. The observer then forces us to ask when a definite outcome enters the story. Every stage exposes another assumption. The atom asks what superposition means. The detector asks what measurement means. The cat asks whether quantum mechanics applies to macroscopic objects. The closed box asks what we should say before an observer learns the result. Opening the box asks why one experience appears. The experiment is simple, because the setup can be described in a few sentences. It is difficult because each sentence touches a foundational question. There is also no reason to think Schrödinger's cat represents the final word on quantum mechanics. Science rarely works that way. Thought experiments help reveal where theories need clarification. Later experiments, new mathematical tools and better technology push the questions further. Today, scientists can prepare and control quantum systems that would have seemed extraordinary to the founders of the theory. Researchers work to preserve coherence in increasingly complex systems. Quantum computing depends on maintaining delicate quantum states long enough to manipulate them. Experiments continue testing how far quantum behavior can be pushed toward larger scales. Every improvement makes the old question more interesting. How large can a coherent quantum system become? Is there any fundamental scale where ordinary quantum evolution fails? Does collapse occur naturally? Can increasingly sensitive experiments distinguish standard quantum mechanics from alternatives? Questions that once sounded purely philosophical can sometimes become laboratory problems as technology improves. That is one reason it would be a mistake to dismiss Schrödinger's cat as an old puzzle that physicists solved decades ago. Parts of the puzzle are much better understood, especially through decoherence. Other parts remain connected to active questions about quantum foundations. The cat is old. The problem it points toward is not. There is a final lesson hiding in the box, and it has less to do with cats than with scientific language. Quantum mechanics repeatedly warns us that words borrowed from everyday experience can mislead us when we use them at scales where those experiences no longer apply. Particle sounds like a tiny ball. Wave sounds like water moving across a pond. Spin sounds like something rotating. Measurement sounds like checking a property that was already there. Superposition sounds like several ordinary situations piled together. Collapse sounds like a physical object suddenly falling inward. Each word is useful, but none should be mistaken for the full theory. Schrödinger's cat is perhaps the greatest example of this problem. The sentence alive and dead at the same time sounds vivid enough that it can replace the real question if we are not careful. The actual issue is not whether an ordinary cat has somehow mastered two biological states. The issue is how quantum alternatives, measurement, environmental interaction, and definite experience fit into one consistent account of nature. Once that is understood, the cat becomes less mysterious, but the physics becomes more interesting. We do not need to imagine a supernatural box. We need only accept that the microscopic world follows rules that do not fit perfectly into the categories our brains developed from dealing with large objects. Those rules can produce superposition. Interactions can spread quantum correlations. Decoherence can suppress interference. Measurements produce stable records. Observers experience definite outcomes. Quantum mechanics predicts those outcomes with extraordinary success. The remaining disagreement concerns what story, if any, should be placed behind that successful structure. Perhaps one day experiments will strongly favour a deeper theory that changes the way we think about measurement. Perhaps objective collapse will reveal itself. Perhaps quantum mechanics will continue surviving every test, and interpretations will remain partly a matter of which conceptual framework we find most coherent. Perhaps new ideas will appear that make today's debate look as limited as older arguments about whether light must be either a classical particle or a classical wave. For now, the cat remains useful because it prevents us from pretending the problem is simpler than it is. So if someone asks you whether Schrödinger's cat is alive or dead before the box is opened, the best answer is not simply both. The better answer is that the thought experiment was created to ask what quantum mechanics allows us to say before a measurement produces a definite macroscopic result. Different interpretations answer that question differently. A real cat would decohere far too quickly to behave like the clean superposition imagined in the simplified story. The point is not the animal. The point is the boundary between quantum possibilities and the ordinary reality we experience. And perhaps that is why the thought experiment has lasted so long. A sealed box seems like such a simple thing. We use boxes to hide objects, store things, move house, and occasionally create an irresistible destination for an actual cat. Yet Schrödinger managed to turn one into a question about the meaning of physical reality. A radioactive atom asks whether something happened. A detector asks whether the event has been measured. A cat asks whether the quantum description can be extended to the world we know. An observer asks what it means to experience one result. Nearly 100 years later, the box is still doing its job, and now, after spending all this time inside it, you can finally open the lid without expecting to find a magical animal suspended between life and death. What you find instead is a thought experiment built to expose one of the deepest questions in quantum physics. How does a world described by quantum possibilities become the definite world we actually live in? That is what Schrödinger's cat really is. Not an answer, not a claim that cats become strange when nobody is watching, not proof that consciousness creates the universe. It is a carefully constructed question about measurement, reality, and the meaning of a theory that predicts nature with astonishing accuracy, while still allowing us to disagree about what is happening underneath those predictions. And if you came here knowing only the famous line about a cat being alive and dead, I hope the box looks a little different now. The cat was never meant to make quantum mechanics sound mysterious for the sake of mystery. It was meant to make us notice that a successful calculation and a satisfying picture of reality are not always the same thing. If you have found this journey through the quantum world interesting, calming, or simply strange enough to keep you company for a while, you can like the video and subscribe to Physics with William, and I would love to know which explanation of the cat feels most convincing to you. Do you prefer one outcome selected by collapse, a deeper hidden reality, many separate branches, or are you perfectly happy letting quantum mechanics predict the experiment without demanding that it provide a familiar picture underneath? For now, though, there is no need to settle an argument that some of the greatest physicists in history could not settle between themselves. The detector can switch off, the box can remain open, and our imaginary cat, having performed considerably more work for theoretical physics than any cat could reasonably be expected to perform, can finally be left alone. Sleep well, fellow traveller, wherever you are listening from tonight.